4, session 2. This is going to be very exciting again. So it will be chaired by Arnob Kundu from SINP Kolkata. So over to Arnob now for taking over the rest of the session. We have, of course, 2 more minutes still to start, but I already hand over to Arnob now.
Okay, thanks, Arun. I guess we can wait for a couple of more minutes, right? Before we start.
Yeah, sure.
I mean, I see people are already gathering in, but just to give them a couple more times. I mean, a couple of minutes more. Okay. Well, maybe we can start 1 minute earlier than scheduled time. All right. So welcome everyone to the 4th day, 2nd session of this workshop. And our first speaker for this session is Andrea Puhm from ECOL, and she's going to tell us about a double copy for celestial amplitudes. So over to you, Andrea.
Thank you. Thanks for organizing this conference and for inviting me to speak. So this talk will be in the context of a program that has been developed over the past couple of years and which attempts to understand quantum gravity in asymptotically flat space, and in particular, where there is an underlying holographic structure. The talk will be mainly based on a paper from July, which was done in collaboration with Eduardo Casali, and which gives rise to the title of this talk. Incidentally, this title also fits very well with the title of the conference, Dual Mysteries of Gauge Theory and Gravity, because the talk will be about a by now well-known, yet still mysterious relation between gauge theories and gravity that goes under the name of double copy, but it will be from the perspective of a proposed dual holographic so-called celestial CFD, which will describe bulk, 4-dimensional bulk physics. Depending on time, I will also discuss earlier work from last year, and then more recent results together with Hernan Gonzalez and Francisco Rojas. So it turns out that quantum field theory scattering amplitudes possess a so-called conformal basis when we replace the plane wave asymptotic states by so-called conformal primary wave functions. Now, behind the scenes here is that the 4-dimensional Lorentz group, SL2, acts as the global conformal group on the 2-sphered null infinity, namely the celestial sphere. And this means that 4-dimensional massless scattering amplitudes can be recast as 2-dimensional conformal correlation functions described by operators inserted on this celestial sphere at null infinity. Now, studying these so-called celestial amplitudes could provide powerful constraints on the quantum gravity S matrix when recast in this basis, but it could also give us new insights into amplitude structures because they highlight certain properties of amplitudes which are obscured in the usual plane wave basis. Now, besides being interesting in their own right, these celestial amplitudes also offer the hope that 4-dimensional spacetime physics may be encoded on the conformal boundary of the spacetime. And this would provide us with a holographic picture for physics in asymptotically flat space. Now, one of the first questions that one has to address is, what are the symmetries of the spacetime, and can they really be identified with those of a proposed holographically dual field theory? And the keywords that come up here are the so-called Bondi, Van der Burg, Metzner, and Sachs group, which provide an infinite enhancement of the Poincaré group. And it can also be further enhanced to a Virasoro asymptotic symmetry group, or even a full diffeomorphism on the sphere. These are interesting questions, and there has been a lot of work on this topic in the past couple of years. But my main focus in this talk will be about properties of these celestial amplitudes. And some of them have been discussed over the past 1 or 2 years. One thing that we learned was that the OPE singularities of usual 2D CFD can be obtained by taking collinear limits of amplitudes. We understand that there are certain factorization properties of these celestial correlators, which follow from the usual soft theorems in quantum field theory. And we have recently obtained some insights on how we can take this program beyond tree level. My main focus here will be on how celestial amplitudes in gauge theory are related to those in gravity. So the slogan here is that gravity is Yang-Mills theory squared. And this is by now a well-known feature of amplitudes, and it has been extended to various theories beyond tree level and even to a nonlinear description. The input that I will need in this talk from the double copy procedure can be summarized in the slide. So I will start with an n-gluon amplitude in Yang-Mills theory, which is described as a sum over graphs. There are these color factors denoted in blue. There are the kinematic numerators denoted in red. And the denominator here is a product of scalar propagators. And the four-dimensional energy momentum conservation is depicted by this delta function here. Now, these color factors in blue satisfy a Lie algebra Jacobi identity. And for the whole rest of the talk, in the context of the double copy, I will remain at tree level. And there we can always find kinematic numerators that satisfy a similar relation. And these are called color kinematics dual or BCJ numerators. So when you have this setting, and if you replace the set of color factors here by another set of kinematic numerators satisfying these properties, then you obtain an expression given down here, which turns out to be none other than a representation for an n-graviton amplitude. So that's the double copy procedure. Now, I would like to know whether this double copy procedure, this relation that squares Yang-Mills to gravity, also holds for these celestial amplitudes, and therefore in the context of holographic, putative holographic CFT that describes this bulk scattering process. But there's a puzzle. So usually amplitudes are described in a plane wave basis, and that basis makes translation symmetry manifest. And the double copy heavily relies on this momentum conserving delta function here. On the other hand, celestial amplitudes are computed in a conformal basis. It makes conformal covariance manifest, but it completely obscures translation invariance. And so momentum conservation is lost in celestial amplitudes. Now, we do expect fundamental properties of amplitudes, such as this double copy relation, to survive a change of basis. But because momentum conservation is lost in celestial amplitudes, it's not clear how this should work. So the goal of this talk will be to show that there does exist a well-defined procedure for a celestial double copy, but it requires a generalization of the usual squaring of numerators. And this entails that we first promote the numerators to generalized differential operators that act on scalar wave functions and then square them. So this is the plan of my talk. I will start by reviewing some properties of celestial amplitudes with particular focus on 3- and 4-point amplitudes in Yang-Mills and gauge theory. I will highlight the similarities and differences between Yang-Mills and gravity, and these become particularly clear when discussing factorization theorems of correlators, which arise in the so-called soft limit. And then I will discuss the generalization of the momentum space double copy to the celestial setting. Depending on time, I will then also discuss some recent results on obtaining celestial loop amplitudes from tree level, and the particular features there that we encountered there will resonate with those that we had to generalize the double copy to. And then I will end with some summarizing remarks. Maybe I should say that I'm happy to take questions during the talk, so if anyone wants to interrupt at any time, please do so. Okay, so let me start with some properties of celestial amplitudes. So I've mentioned that I will discuss massless scattering processes where stuff comes in from the past null infinity and then goes out to future null infinity. The scattering matrix is labeled by 3 parameters. I take them to be a point z bar on the 2-sphere at null infinity, and a scale given by the energy omega. And then there's also the helicity of the particles involved. Now, 4-dimensional scattering amplitudes obey 4-dimensional Lorentz symmetry, and this acts on the celestial sphere at null infinity as the 2-dimensional global conformal group. And we can therefore recast the S matrix as a correlation function of operators O that are inserted at points z bar on the celestial sphere, and which are labeled by the quantum numbers of the global conformal group, namely the scaling dimension or the conformal dimension delta and the spin j. So specifically, I will be focusing on scattering of gauge bosons in four-dimensional Minkowski space. The coordinate vectors will be denoted by x, and the states will be labeled by this momentum null vector k, or equivalently by the scale omega, and the null vector q that points to zz bar on the celestial sphere. A convenient presentation for this null vector is given by this expression. And in terms of this expression, the polarization vector and tensors of particles with spin can be described as z derivatives of this null vector for positive helicity and a c bar derivative for negative helicity. Now the polarization tensor for spin 2 particles will be given by, will be taken to be the square of these polarization vectors of spin 1 particles. So with that, the basis of scattering amplitudes is given by spin wave, one wave functions of the polarization vector times the plane wave e to the I k dot x in Lorentz gauge. So that means the momentum vector dotted into the polarization vector gives 0. And then the spin 2 wave functions are similarly given by the polarization tensor dotted into and the plane wave e to the I k dot x in harmonic or redondo gauge. So now I want to move on from this momentum basis for scattering amplitudes to the so-called conformal basis, where the labels are now the points on the sphere and the conformal dimension delta and the spin j, which will be identified with the helicity of the four-dimensional particles. So this change of basis can be achieved by a so-called Mellin transform in the energy of the particles. So that means we integrate from 0 to infinity over the energy with this particular weight factor of the energy to the power delta minus 1. Via that integral transform, we can go from momentum eigenstates e to the I k dot x to boost eigenstates, which are given by 1 over the null vector q dotted into the spacetime vector x to the power of the conformal dimension, and it comes with some normalization that depends on the conformal dimension. So these wave functions phi delta are now spin 0 wave functions in this new conformal basis. I can then construct spin 1 wave functions by attaching the appropriate polarization vectors and spin 2 wave functions by attaching the polarization tensor. And this will be denoted by V delta, respectively. Now, starting from a basis of plane wave functions of finite energy, via this integral transform, we obtain a new basis of wave functions, which are now constrained to, so finite energy wave functions give the constraint that this conformal dimension has to lie on the so-called principal continuous series of the Lorentz group, which means that delta has to have real part 1 and any real imaginary part. So that's the constraint coming from finiteness of the plane wave basis. We also have a kind of state operator correspondence because massless particles that enter and exit the space-time can be described by operators inserted on the celestial sphere. And while in the plane wave basis, translation symmetry is manifest, in the new conformal basis, conformal symmetry becomes manifest, while the other one gets respectively obscured. So let me be very specific here. So these wave functions phi delta that I just introduced via this Mellin transform behave under SL2Z transformations, under Lorentz transformations in the following way. So Lorentz transformations lambda act on a space-time vector, and then the action of the Lorentz group on the celestial sphere is given by this Möbius transform in the angle coordinates z and z bar. And from this expression, we see that these wave functions phi delta transform as conformal primaries in a two-dimensional theory, where this conformal dimension, as I said before, is restricted to lie on the principal series of the Lorentz group. Now, similarly, for spin 1 and spin 2 wave functions, we get conformal primaries. But the thing here is that these wave functions that are introduced before, these wave functions V, do not themselves transform properly under SL2Z transformations, but I have to add a pure gauge and a pure diffeomorphism term to these wave functions, and then they transform as conformal primaries. Now, we will not need to bother with these pure gauge and pure diffeo terms written in blue, but just to point out that these terms are very important to connect this whole discussion of celestial CFT and purity holographic dual to the topic of asymptotic symmetries of asymptotically flat space from this perspective of this two-dimensional theory. Okay, so we have transformed now the basis of plane wave functions to conformal primary wave functions. And now what about amplitudes? So here we should take a Mellin transform of each of the external particles. So in an n-point amplitude, those are n such Mellin transforms. And the four-dimensional amplitude given by this stripped amplitude expression and the four-dimensional energy momentum conserving delta function then will be mapped to a two-dimensional correlation function of operators inserted on the celestial sphere. And similarly to the asymptotic states, these amplitudes transform covariantly under the 2D global conformal group, given by this expression, which runs again from 1 to n. Now, let me emphasize again that the conformal dimensions of all these particles involved is complex. So this is a different or rather mysterious feature of this putative two-dimensional celestial CFD, which is different from the usual vanilla garden variety CFDs that we have, for example, in ADS CFD correspondence. And let me also mention again that the spins of the particles are identified with the helicities of the four-dimensional particles. Okay, so now we have the basis of wave functions, the celestial amplitudes, and now let me just give some examples. So let me take some 3-point amplitudes in Yang-Mills theory and gravity. I will focus on MHV amplitudes. Zij will denote the difference of 2 points on a celestial sphere. And instead of the conformal dimension delta and the spin j, I will also be using the weights h and h bar. Now, the 3-gluon MHV amplitudes is given by this expression in the frequencies and the differences of points Zij. Similarly, the gravity amplitude. And after a Mellin transform of the 3 external particles in each of those cases, I obtain the celestial amplitude. Now, focusing on the part in black here in the denominator, this is a very familiar expression, namely, it is the expression of a 3-point correlator in a 2-dimensional CFD, where these HIs are just the weights of the operators that are inserted. And those are, of course, different for Yang-Mills theory and for gravity. What's rather different from usual CFD is the terms written in color. So we have in blue some delta function terms that constrain the differences of positions of the anti-holomorphic coordinates z bar ij, and then some step functions that constrain their ratios. And this follows, this is a remnant of the four-dimensional energy momentum conserving delta function. And furthermore, we have these leftover integrals in red, which are of a different nature. So in Yang-Mills theory, this remaining integral in omega-3, this remaining Mellin integral, is the integral representation of a delta function. And this delta function constrains the range of the imaginary part of the conformal dimension of all the involved particles. Now for gravity, this integral is divergent, but we can go to string theory in order to soften this divergence. But we can also, if we want to remain at tree-level classical gravity, there are some amplitudes which are finite, and those amplitudes have to involve some gravitons that have real conformal dimension rather than a complex one. And we can describe this by an analytic continuation of some of the lambdas, the imaginary parts of the conformal dimensions of the particles involved. Now, let me also mention that there is a nice squaring relation between the 3-point amplitudes in Yang-Mills and gravity. But after we move to this new conformal basis, there is no apparent way that these two-dimensional correlators square into each other. So now let me also discuss 4-point amplitudes. It turns out that a celestial 4-point amplitude can be written in the form given here. So there is this universal prefactor in the Zij's, Z bar ij's, and the conformal weights. And then there's this conformally covariant expression F up here. That's a function of the cross ratios Z. And these cross ratios are given by, well, I chose it to be this particular cross ratio, Z12, Z34 divided by Z13, Z24. Now, explicit examples, MHV amplitudes for Yang-Mills and gravity. Those are given by these expressions here. After Mellin transform on the 4 particles, we get an expression for this expression F. That is the usual expression from two-dimensional CFT, namely a function of the cross ratio z and 1 minus z to some powers. But there's also these colored terms, which are again very different from usual CFT, and those provide a constraint, a reality constraint of the cross ratios. It constrains the range by this step function. And then there are again these red integrals, which in the case of Yang-Mills theory can again be written as a Dirac delta function constraining the conformal dimensions. But in gravity, again, it's divergent. Yet again, we can go to string theory, or for certain amplitudes, we can do these analytic continuations. Now, there's again a relation that takes a Yang-Mills amplitude squared and gives gravity. Now, it seems from these conformally covariant expressions that there's some kind of squaring going on. But we also have these color terms in red and blue, which seem to obstruct a full squaring of the celestial amplitudes. So the purpose of my talk will be to show how Yang-Mills and gravity obey this double copy relation for the celestial correlators. But before doing so, let me mention another curious property of celestial amplitudes, and which arise in the context of so-called soft theorems. So I've shown you that a basis of finite energy plane wave functions gets mapped to these conformal primary wave functions, where the conformal dimension is restricted to take this form. But since we're integrating over the energy, it's not clear how the energetically soft limit of quantum field theory scattering amplitudes, which consists in taking the energy of an external massless particle in an amplitude to 0, it's not clear how that will survive in the new conformal basis. In the new basis, the infrared and ultraviolet are mixed, and the notion of energy has completely disappeared. And in its stead, we have the notion of conformal dimension via this integral transform. So it turns out that universal factorization properties of amplitudes, which arise in the energetically soft limit, of course, survive this change of basis. But what we should do now instead is take the so-called conformally soft limit. And that entails taking one of the weights, h or h bar, to 0. Now, this is the case for Yang-Mills amplitudes, but it turns out that when going to gravity or to more general amplitudes and to subleading orders in the energetically soft expansion, that there's actually a bigger story here. And the story is that when taking the energetically soft expansion in omega going to 0, where the amplitude factorizes in terms that start with an order 1 over omega pole and then an order 1 term, that these orders of omega are mapped to poles of the celestial amplitudes that are at certain integer values of the conformal dimension. So, for example, for the leading energetically soft pole, the corresponding celestial amplitudes has poles at the value of the conformal dimension being 1. And then there is a series of this order in omega, which gets mapped to different conformal dimensions. As an example, let me tell you about the soft gluon and the soft graviton theorem and how it maps from the plane wave basis to the conformal basis. So on the one side, we have this energetically soft limit, while on the celestial side, we should take the conformally soft limit of taking the conformal dimension to 1. That's the leading soft theorem. For the soft gluon theorem, it means that when we have an n gluon amplitude and we take the energy of one of these external massless particles to 0, the amplitude factorizes into an n-1 point amplitude and a soft pole. And the soft pole comes with a universal factor, the soft factor given here in terms of the differences of points z on the celestial sphere. Now, the analogous statement for celestial amplitudes is that we should take the conformal weight to 0, which coincides in the case of Yang-Mills theory with taking the conformal dimension delta to 1. So then we have an n-point correlator that factorizes into an n-1 point correlator times a new soft pole, but now it's a soft pole involving the conformal dimension rather than the energy. And it turns out that the universal soft factor associated to this soft pole takes exactly the same form as in the momentum space energetically soft theorems. For gravity, the story is a bit different, and that highlights a difference between Yang-Mills theory and gravity for celestial amplitudes. So in momentum space, Weinberg's soft graviton theorem follows similarly as the soft gluon theorem, but now the soft factor associated to the soft pole comes with an explicit factor of the energy omega. And that has as a consequence that when we Mellin transform over all these energies, the corresponding conformally soft graviton theorem for celestial amplitudes takes a little different form. And the form it takes is as follows. We start from an endpoint celestial graviton correlator. We take this limit of delta of one of the graviton operators inserted to 1. But now the amplitude factorizes not only into an n-1 point amplitude times conformal soft pole, but there is in these lower point correlators, we have to shift one of the conformal dimensions of the operators. And then it will be summed over, and we have to shift in each of those lower point amplitudes, we have to shift one of the operators. And this really follows from the explicit appearance of energy in the soft factor for the graviton amplitude. And this can be understood in terms of conserved currents inserted into correlators. These are related to these blue terms, these diffeomorphism and gauge terms in the asymptotic states. In Young-Mills theory, this is these conserved currents inserted are just proportional to these conformal primary wave functions. And the OPE between this conserved U1 current gives this nice OPE with some operator of energy omega, which turns into the same statement of an operator of dimension delta in the conformal basis. But for gravity, the corresponding OPE, which now involves this so-called BMS supertranslation current, this is not the primary, it's a descendant. And the OPE with an operator of energy omega has an explicit factor of the energy omega, which turns in the conformal basis into the statement that the dimension of the operator has to be shifted by 1 in the OPE. So this describes a difference, yet another difference between Young-Mills theory and gravity amplitudes. And we will encounter this difference, another such difference when now moving to the celestial version of the double copy. Maybe I should stop at this point and ask if there are any questions on celestial amplitudes and their properties before changing gear.
So, Andrea, there are already 2 questions. Would you like to take them?
Sure.
I can read out for you if you want. So the first question is from Sujay Ashok. He's asking that are the 3 and 4 point functions consistent with conformal bootstraps, specifically for the OPE coefficients?
So, so far, this program has been bottom up. It has taken amplitudes and inferred properties of the correlators in the celestial sphere via the Mellin transform and taking certain limits in amplitudes and seeing what they imply on the correlator side. But there has been a recent paper that relates higher point to lower point correlators via the OPE, and it's consistent. So from a bootstrap perspective, and that's consistent what we know so far. Maybe you are surprised by the appearance of these delta functions here in the 4 point and the 3 point amplitudes. This is a curious property that you actually don't really see if you start with an n-point amplitude and you take the collinear limit and get the OPE. So this is a curious property of lower point amplitudes that you don't necessarily see if you take an n-point correlator and take the OPE to get an n-1 point correlator. But what I can tell you, I didn't show this, but in this conformally soft limits, which relates, let's say, 4 point to 3 point correlators, you can explicitly show that if you take the conformally soft limit of, say, this gluon or graviton amplitudes, which have these delta functions and these red amplitudes, these red integrals here, that the conformally soft limit really lands you on these 3 point functions with these different delta functions and integrals here. So this is perfectly consistent. But it's still a mysterious. It's still mysterious by comparing it to vanilla CFTs that we know. So we don't yet know what this CFT is.
Okay.
I hope this answered the question.
Sujay, if you have any follow-up comments or questions, probably you can go ahead.
I was just wondering if the products of these delta functions make sense. Because you would imagine something becoming singular when you take products of these 2-3 point functions somehow. But you say
so I think this recent paper that I referred to did not specifically look at 4-2-3. Because for the OPE, you don't, I mean, you can look at higher point amplitudes where you don't have this specific delta function in the Zs.
Okay.
So this comes from, this is a remnant from the momentum conserving delta functions, which is 4 in 4 dimensions. So that's why there are more delta functions for 3-point and less for 4-point. But the conformally soft limit really explicitly takes these delta functions and lands you on the delta functions for the 3-point amplitude. So this conformally soft limit is perfectly consistent, and by massaging the expressions, you really see that you get those delta functions out.
Okay. Thank you.
There was another question?
Yeah, there's another question from Oyon. Oyon, would you like to ask it?
Andrea, so my question is that you said that CFT transformations, the conformal transformations have to be augmented by some gauge and Diffie transformations for it to be transforming in a primary in a nice way. So is there some augmentation of the word identities and such, and you can relate soft theorems to word identities in this basis that you're talking about?
Yes, indeed. So the soft theorems are related to word identities, and the word identities are related to these conserved currents, J and P, that I've shown you here. And indeed, you need, in order to the wave functions that you just obtain from Melian transforms of plane waves and attaching polarization vectors, you have to add this pure gauge and pure Diffie terms. Okay, so from the point of view of the amplitude itself, if you just insert this, these conserved currents, yeah. So okay. So yeah. So these pure diff and pure gauge terms are important in understanding, having the complete picture for the relation between these asymptotic symmetries and the word identities to the soft theorems. You can show that. So there is one thing. There is the Goldstone modes associated to the spontaneously broken asymptotic symmetries, and then there are the symplectic partner of these Goldstone modes, which need to be there in order to have a memory effect. So the soft photons and the soft gravitons and soft gluons, to understand them in the conformal basis, it's important to have these pure Diffie and pure gauge terms. And this is a bit subtle. So these zero modes where you take lambda to 0, delta to 1 are a bit subtle, but we understand them now.
Thank you. Thanks.
So this is a whole new story, and it opens a whole other can of well, interesting stuff. But here I want to focus. I decided not to talk about this and instead focus on the properties of celestial amplitudes between Young-Mills and gravity. So if there are more questions, please, you can ask me again after the talk or in the Slack channel. Okay, so now let me move on to the celestial version of the double copy. So as I mentioned, the momentum space double copy makes heavy use of this energy momentum conserving delta function in the momenta. And in order to generalize this to a setting that lacks momentum conservation, it's convenient to rewrite the 4-dimensional delta function as a space-time integral over these plane waves here. So this integral representation of the delta function will be very useful in generalizing the setting to when we don't have explicit momentum conservation. And this was used in a procedure that was developed in this paper from 2017 in trying to generalize the double copy to plane wave backgrounds. So besides the interest in understanding the squaring relation from the perspective of this 2-dimensional celestial CFT, it's also interesting to study the double copy because it requires a generalization to the curved space double copy as provided in this paper, but it comes without the complications of actually having curved space. So this sits somewhere in between the flat space double copy and the curved space double copy. And while it is obvious, I want to highlight that one important point here is that we pull down the null momentum 4 vector by partial derivatives, and these null vectors are space-time independent. And we will have to generalize this and go away from this space-time independence of momenta in order to arrive at a celestial version of the double copy. So this is to keep in mind. So now let me just rewrite the usual double copy in momentum space by not using the energy momentum conserving delta function explicitly, but keeping the space-time integrals implicit. So we have these spin 1 and spin wave 2 wave functions that I introduced before in the plane wave basis. I attached a color factor for the Young-Mills wave functions. And here we have the 3-point vertices for Young-Mills and gravity. So now if we plug in the explicit expression for the wave functions, we get these expressions in the momenta and the polarization vectors. And it turns out that if we take the gravity 3-point amplitude and we massage the integrand, essentially by integrating by parts, since we are not allowed to use momentum conservation now. So we integrate by parts, and then we end up with an expression which turns out to be nothing other than the square of the integrand for the Young-Mills amplitude. So once we strip off this common factor of the wave functions e to the I k dot x, we see that the integrand in Young-Mills theory squares into the integrand of gravity. So that's just a double copy, but now rewritten by having explicit space-time integrals left over. So here we haven't gained anything because we could just do this space-time integration explicitly, and we end up with the usual double copy statement for 3-point amplitudes. But we will, the reason why I've gone through these exercises, because now we will try to generalize this to celestial amplitudes. So here we have, instead of the plane waves e to the I k dot x, we have this scalar wave functions phi, which are given by this Mellon transform. And remember that the polarization tensor is given by a product of these polarization vectors. So in order to mimic what happens in the momentum space double copy and general in momentum space, we define so-called celestial momenta to be simply the equivalent of the pulling down of the momentum vectors k in the plane waves when we act with partial derivatives. So the celestial momenta are given by this null vector q divided by 1 power of this factor q dot x. And they also come with this conformal dimension delta. Now, let me try to naively double copy the celestial Young-Mills and gravity amplitudes. So the Mellon transform of the amplitudes that I showed you before are given by these expressions. And essentially what happened is that the plane waves e to the I k dot x got replaced by these wave functions phi. And the little momenta, the little k's, the momentum space momenta, got replaced by the celestial momenta capital K. Now, let's try to integrate by parts and massage the gravity integrand. The question is, does this gravity integrand become the square of the Young-Mills integrand in this celestial amplitudes? It turns out that this is not the case. So the celestial graviton amplitude with this celestial momenta capital K does not correspond to a square of the Young-Mills, celestial Young-Mills integrand. And the reason for this failure is the space-time dependence of the celestial momenta. So in the plane wave basis, we had that the partial derivatives acting on the momenta vanishes, while here we get this explicit space-time dependent term that comes with this factor 1 over delta. And these explicit terms that arise when trying to integrate by parts the gravity integrand spoils the naive double copy for celestial amplitudes. So we have to come up with something better. So this is our proposal. What we propose is that you should promote the celestial momenta capital K that show up in the numerators to differential operators, curly K, which are defined to act on the conformal wave functions phi in the following way. So they give back the celestial momentum, but only if the labels of the differential operator and the wave functions are the same. So in this sense, these differential operators, they act similarly to the partial derivatives, but they're different because they keep track of the particle labels. There is an interesting representation of these differential operators given by this exponential in derivatives in terms of the conformal dimensions of the ith particles. And this representation is the action of the translation generator of the Poincaré algebra that acts on the coordinates of the ith particle. And that has been discussed in the symmetries of celestial amplitudes in this paper from 2018. So with this prescription, let me now return to the 3-point amplitude and see if the double copy works. So now we have replaced the numerators by some operator capital curly N, which instead of the celestial momenta K involves now these differential operators curly K, and those act on all these wave functions phi. Now, when explicitly carrying out the action of these operators on the wave functions, what will happen is that we encounter extra terms. And these extra terms, they only show up when the operator has the same label as the wave function. On the other hand, we have the gravity enumerator, which we also promote to an operator, and acting on wave functions phi. And then we can perform integration by parts. And what happens there, which we encountered already before, is that when partial derivatives hit the celestial momenta, they give these extra terms with factors 1 over delta. And the nice thing is that these extra terms that show up when celestial operators with the same particle labels as the wave functions and partial derivatives acting on wave functions by integration by parts, these extra terms that show up precisely cancel. So indeed, if we take our double copy prescription, where we promote the gravity numerator to an operator and the Young-Mills numerator to an operator, the Young-Mills numerator squared acting on the wave function gives exactly the gravity numerator operator acting on the wave function. So the celestial 3 gluon amplitude double copies into the celestial 3 graviton amplitude. Okay, very nice. So this double copy procedure works. But I've only done 3 points. It would be more satisfying if this carries over to higher multiplicity. So let me now discuss this for 4-point amplitudes. This is a bit more complicated because now the Young-Mills 4-point amplitude has contributions from the 3 different channels S, T, and U. And there's also this contact term. And the features that we will need is that the propagator in these channels, which is just given by e to the I k dot x minus y divided by k squared integrated over k, satisfies these properties. So the box with respect to the x coordinate and with respect to the y coordinate just give this delta function in x minus y. And in order to move on and to discuss the double copy, what we will do is we will open up this contact term, which depends only on one spacetime point, such that it looks as if it depends on 2, but it has this explicit delta function. And then we will massage the expression that we obtain in order to split this contact term into contributions to the S, T, and U channel, because they come with the same color factors. So by doing a bit of massaging, we will end up with the 4 gluon amplitude given by this expression. We have the propagator, and then we have 3 terms for the corresponding channels. Let me unpack this a bit. So these capital phi's are just the plane waves in the respective channels. The terms in blue here are the color factors obeying the Jacobi identity, and the terms in red are the kinematic numerators, which are given by these ugly expressions because we have left the spacetime integrals explicit. But they just depend on the polarization vectors and the momenta. Now, by replacing these color factors by another set of numerators, we obtain an expression that has these numerators squared, and this is nothing but the double copy statement for 4-point amplitudes. So this 4 graviton amplitude is a double copy for the Young-Mills amplitude. And by double copy, I mean in each channel, there is a squaring going on once we have stripped off the wave functions phi. So now let's see if we can use our double copy prescription to also get a relation for the corresponding Mellin transform celestial amplitudes. So the Mellin transform of the 4 gluon amplitude is given by a same structure. And effectively, what we do is we replace the wave functions e to the I k dot x by the conformal wave functions phi and the little momenta by the celestial momenta capital K. Then again, we have these capital phi's now with a tilde because they're now the Mellin transformed plane waves given by the expressions in phi. The blue terms are again the color factors, nothing changed there. And now these kinematic numerators and tilde are given not by the little momenta k, but by the capital momenta. And so therefore these depend on the spacetime points. And moreover, because those are exchange diagrams, they depend on 2 spacetime points, x and y. Now, if we try to just replace the color factors by another set of numerators and tilde, we get an expression, but this expression is not the celestial for graviton amplitude. And essentially the failure is that the numerators depend on space-time. So how do we make this work? So we replace the celestial momentum capital K by these operators curly K. So that means we replace these numerators and tilde by some operator valued numerators. And then we replace this color factor C by another set of these operator valued numerators. And the expression that we then get is precisely the one for the celestial for graviton amplitude. Now, here I've just given the prescription, but in order to check that this celestial 4-point amplitude is really the Mellin transform of the 4 graviton amplitude, we just need some properties of the Mellin transform. So the original 4 graviton amplitude depends on the energy of the particle in a polynomial fashion. And when we Mellin transform, we get essentially 2 cases. One is where the Mellin transform is linear in the energy, is just a 1K, and one where it's quadratic in the same energy, Kj, Kj. And in this case, we have these extra factors appearing, and these extra factors appearing are precisely what we need in order to show that the expression where we have this operator valued numerator squared is precisely the Mellin transform of the 4-point graviton amplitude, which had the original momentum space numerator squared. So also the 4-point double copy for celestial amplitudes works given our prescription. Now, I think I'm out of time. Let me just finish saying 1 or 2 things, which is that this way of presenting the amplitudes with these operators acting on wave function also gives a nice presentation of amplitudes with spin as obtained from scalar amplitudes. So we can actually pull out all these operators in front of the spacetime integral and express celestial 3-point amplitudes in Young-Mills and gravity by some operators acting on scalar amplitudes. And similarly, for the 4-point amplitudes, we can write the 4-point Young-Mills and gravity celestial correlators as operators acting on integrals of scalar wave functions in each of those channels S, T, and U. So this is a nice presentation of amplitudes with spin in terms of scalar amplitudes. Okay, so I'm out of time, so let me just skip to the conclusion. So I showed you that celestial amplitudes are obtained from a change of basis of the asymptotic states. For 4-point amplitudes, these take in particular this universal expression in terms of conformally covariant factor F in terms of the cross ratios. There are unusual features in these correlators that have to do, first of all, with the complex dimension of the operators, and also all these delta functions that appear in that restrict the angles of the 2-sphere and the sum of the conformal dimensions. The energetically soft limit becomes obscured when Mellin transforming over the energy, but in its stead, we have the conformally soft limit, which mimics universal factorization properties. I've shown you that one can obtain a celestial double copy by promoting momenta to operators and therefore the numerator squaring to unsquaring of operators. And what I did not have time to discuss is that you can also obtain celestial loop amplitudes from tree-level amplitudes. And the way to do this is by the action of an operator. And this operator is somewhat related to the one that shows up in the celestial double copy. So thank you very much for your attention.
So thanks a lot, Andrea. So let's unmute ourselves and thank her for a wonderful talk. We have about 10 minutes for questions and discussions. And if it takes longer, then that can continue in the Slack link. So the floor is open for questions.
Hi, Arnav, I have a question. Can I ask?
Yeah, sure. Go ahead.
Andrea, hi. So yeah, one of my questions was that this, I mean, could you think of the double copy as initially coming from the biadjoint scalar where you replace one of the color factors with the n Young-Mills operator, the Young-Mills amplitude coming from the biadjoint scalar by replacing one of the color factors with your operator for the Young-Mills amplitude?
On the momentum side, of course, yes.
Yeah.
But on the celestial side, I haven't done it, but I would expect this to work in a similar way as here. I should also, so yeah, I think this should go through. And I should also say that this prescription should carry over to any multiplicity in principle, because, and instead of having these 2 spacetime integrals, you can just take over this prescription to work for n-2 spacetime integrals. And do the replacement of the momenta by these operators.
Mhm.
It's probably a lot more work to show this for higher points, but in principle, this should carry over.
I see. Thanks. So in that context, do you have any thoughts on KLT in the celestial basis? Is there a way to?
Yeah, that's also a very interesting question. I haven't had time to think about this, but yeah, this now opens a whole zoo of questions, because there's been so much work and so many interesting results on a double copy, and of course you can ask, do all these results carry over to celestial amplitudes? Are there any surprises there? KLT would be an interesting question to study for celestial amplitudes. There has been a bit of work for celestial string amplitudes, but not too much. So there is also room for a lot of interesting problems to tackle there.
Okay, thanks.
Any more questions or comments?
Anyone has a question on loops?
Well, yeah, I was going to say that if there are no more questions, perhaps you can elaborate a bit more on the things that that you had to sort of rush through in 5 minutes or so.
Happy to. Thank you for the question. So what I didn't get to talk about is celestial loop amplitudes. So far, most of the discussion of all the properties of celestial amplitudes over the last 2 years or so, 3 years, has been for tree-level amplitudes. But now we also have results about loop-level amplitudes. Here, a simple place to start would be planar n equals 4 super Young-Mills and look at the 4 gluon MHV amplitude. So in the momentum basis, the one loop amplitude can be written as the tree-level amplitude times a one loop factor and a factor of the 't Hooft coupling. And this one loop factor comes with some function that depends on the dimensional regulator. Here I've chosen dimensional regularization, where the polarization vectors and external momenta remain in 4 dimensions, but the internal momenta are in 4 minus 2 epsilon dimensions. And so we have this infrared divergent factor F. And then we have a factor that depends on the energy given by this Mandelstam variable T to the power epsilon. Now, you can ask, okay, if I Mellin transform this expression, can I get the celestial one loop amplitude, and what does it look like? So this is a 4-point amplitude. So I've already shown you that the general form that it takes is this. But now this conformally covariant factor F, while in the tree-level amplitude, it was given by the expression here in black. At one loop, the difference to the tree-level amplitude is given by these terms in red. And so besides the infrared divergent piece F and another factor of the coupling, we also have this shift here in the sum of conformal dimension lambda. So this is just the sum of all the imaginary parts of the conformal dimension. And this I is just the integral that gives us a delta function for the conformal dimension in Young-Mills theory. So at tree level, this was finite because tree level Young-Mills is marginal convergent, and we can write this energy integral as a delta function. But now at one loop, this argument got shifted, and so this Mellin integral is no longer convergent. But there's a nice way of writing this in principle divergent integral, namely as the original integral that can be written as a delta function in lambda and an operator that acts on it. And this is related to the operator that I've showed you before, this celestial operator curly K. It also has this d by d lambda or d by d delta. But here at one loop, we also have the regularization factor epsilon here. With that, we can then write the celestial one loop amplitude in a factorized form as the momentum space amplitude. Namely, I start with the celestial tree level amplitude, and then I act with this one loop operator given by essentially this d by d lambda expression, and obtain the celestial one loop amplitude, which has this integral with shifted argument. So this is a nice way of depicting celestial loop amplitudes, and it shows that the factorization that's present in the momentum space amplitudes carries over, but the way it carries over is in the form of an operator statement. So an operator acting on the celestial tree level correlator gives the celestial one loop correlator. And there's a prefactor here that's just a correlator for scalars, which takes care of some of the shifting of conformal dimension that this operator gives. Now for plane n equals 4 Young-Mills, super Young-Mills, there's actually a nice story. You can actually exponentiate all the L loop amplitudes into the so-called BDS formula. So if you sum up all the one loop factors, this expression exponentiates. And you can show that this exponentiation also carries over to celestial amplitudes. But here it's again in the form of an operator statement. So all all loop amplitudes are given by operators acting on the tree level one, and the summing up of all these operators exponentiates into this operator P here acting on the tree level amplitude. So that's all that I wanted to say about loop amplitudes. And the connection to the celestial double copy is that similarly, we have this action of this differential operator acting on so here we have tree level and we can go to loops with this operator. And in the double copy, we had a scalar amplitude and an operator acting on it to give Young-Mills and gravity. So this is a nice way of presenting these different kind of amplitudes, starting from tree level and low spin.
So thanks a lot, Andrea. So I guess let's thank her again for a wonderful talk.
Thank you for having me.
Questions can certainly continue in Slack. So let's just thank her. So now we have to shift to the second talk. I would request Daniel to share his screen. Yes, perfect.
Okay.
Okay. Yeah, we are just right on time. So let's begin. The second talk of this session is by Daniel Grumiller from Vienna, and he's going to tell us about lower dimensional holography. So over to you, Daniel.
Thanks. So let me also start by thanking Ayan, Suresh, and Tanay for organizing this e-conference in Chennai and for inviting me. I'm not going to start preaching to the choir, so everyone in this conference, I guess, agrees that holography is great and of interest. So I'll just going to focus on one aspect. So the holographic principle is a promising idea to define quantum gravity, and ADS-CFT in particular allows to define quantum gravity by its CFT dual. A question that many of us have been asking in the past decade or decades is holography more general? So in particular, are the lessons that we've drawn from ADS-CFT generic, or are some of them particular aspects that only apply to ADS-CFT? Also, are constructions from string theory necessary, or is holography a principle that somehow transcends string theory? Another important question is the holographic principle applicable to our universe, or can we apply it only to spacetimes that asymptote to negative curvature? And if not, does it work also in flat space, so in asymptotically flat spaces, or in asymptotically positively curved spaces like the zeta space? A keyword that appears in many approaches to quantum gravity is the emergence of spacetime. I guess most people working in quantum gravity agree that spacetime is an emergent concept, but what we may not completely agree on is how precisely it does emerge. And holography should tell us this. Yet another concept I want to briefly mention is the difference between doing holography in spacetimes that have asymptotic boundaries, like asymptotically ADS, or doing holography in finite patches, so quasi-diamond holography or near-horizon holography. And in order to address these and many other issues, it's nice to have explicit examples available where we can study all these questions. So we need some hands-on models to test holography and our ideas in holography. So the main simplification I'm going to cover in my talk is to consider lower dimensional models. 2D gravity are the simplest class of models that have horizons. And the most famous example is the Chekif-Teitelbaum Sachdev-Yeaki-Taif correspondence. And 3D gravity provides the simplest Einstein gravity model, and the most famous holographic correspondence is the ADS3 CFT2 correspondence. Now, despite of the simplicity of these low dimension models, there is some genericity to them because many string compactifications have ADS2 or ADS3 factors. So the goal of my talk or lectures today is on the one hand to provide a quick intro to low-dimensional holography and to focus on recent developments. So usually I like my talks to be sharp and focused, but not today. So today I'm taking a bit the broader perspective. And since the talk is recorded and available on YouTube, on some occasions I'll just display information, but not comment on it. So I'll provide links in some cases. So those people who are watching this offline can then pause the video and just click on the link if they're interested in that information. Okay, so let's start with 2 dimensions. So why 2-dimensional gravity? Well, 1 + 1 is the lowest dimension where you have light cones, horizons, and black holes. And it's also the lowest dimension where you have curvature and interesting topology. And the lowest dimension where you have boundary dynamics. So the boundary still has 1 dimension, namely time, and therefore you can have edge states. Moreover, it is 2 factors are ubiquitous in the near horizon limit of extremal black holes. So the classic example is near horizon, extremal horizon Nordstrom, which is Robinson-Bertotti, or it is 2 crosses 2. And that has led to many applications concerning black hole entropy and attractor mechanism. So the upshot of this slide is that 2D gravity is simple, but not too simple for black holes and holography. Okay, so which 2-dimensional theory of gravity should we consider? Let me start by saying what is not meant here. So in some sense, string theory is a 2-dimensional theory of quantum gravity because the string worldsheet is 2-dimensional, but this is not what I'm meaning here. So in a string context, 2D gravity refers to the dimension of the target space. We cannot use the Einstein-Hilbert action in 2 dimension because that yields no equations of motion, but just the Euler characteristic, so we do not use it. Now, what should we use instead? Well, you can do something very silly. You can stupidly count the number of gravitons and take the limit d going to 2. You get a nonsensical answer of -1, but this answer at least suggests what you should do. So if you want a theory that has 0 local degrees of freedom, like 3D Einstein gravity, then you have to add 1 degree of freedom to 2D gravity. So we add a scalar field known as dilaton. And the simplest example of these models is the Chakif-Teitelbaum model. So basically, you are multiplying the Einstein-Hilbert action by a scalar field, which I'm always calling x here. So in this case, the equations of one of the equations of motion is just the Ricci scalar is constant. But that choice is by no means unique. So there's infinitely many other 2-dimensional gravity models. So let me give you some examples. You can get 2D gravity from dimensional reduction of higher dimensional gravity. So for instance, take the S-wave sector of d-dimensional gravity. You decompose the d-dimensional metric into a 2-dimensional part and the d-2 sphere part with some factor x that captures the surface area of the 2 sphere. You insert this into the d-dimensional Einstein-Hilbert action, integrate out the spherical part, and end up with this 2-dimensional gravity model, which again has a dilaton field. And the solutions of this 2-dimensional model are in 1-to-1 correspondence with the Schwarzschild-Tangalini black holes in higher dimensions. Yet another way to get 2D gravity in a somewhat natural way is to take the d to 2 limit of d-dimensional Einstein gravity, but do a singular rescaling of Newton's constant. So if you don't rescale Newton's constant, you get the issue I mentioned before. You have a bulk action that has no equation of motion. But if you do a singular rescaling of Newton's constant and take the limit epsilon to 0 in a suitable way, you can get a non-trivial result, namely Liouville gravity. Okay, and as a final example, let's consider 2D gravity as the target space description of 2D strings. So if you consider the conformal invariance of the worldsheet action, you know that for consistency, the beta functions have to vanish, and you can interpret the vanishing of the beta function as equation of motion coming from some target space action, and the 2-dimensional target space action is this one. So this is again a 2D model that has a dilaton and a metric. And that led to lots of interesting discoveries in the early 90s concerning black holes in 2D string theory, starting from the seminal work by Mandal, Sengupta, and Vadia. So the summary of all these avenues is this generic action for 2-dimensional dilaton gravity. And the bulk input that we need is a kinetic potential U of x, a dilaton potential V of x, and the value of the 2-dimensional Newton's coupling G2. So I'm not going through this whole list. This is just to show you that many explicit choices for these kinetic and self-interaction potentials were done in the literature, and they lead to black hole solutions with various different asymptotics, ADS, the sit asymptotically flat, or some other asymptotics. Okay, so let's proceed with asking questions. So the next question is how? How should we formulate 2D gravity? Well, there are at least two different formulations that I want to present. One is the second order formulation that we've just seen, but now let me add boundaries. So the bulk part we've already covered, and the boundary terms comprise the Gibbons-Hawking-York-like term for having a well-defined theory shift problem. There's a kinetic counter term in case the boundary is not a dilaton isosurface. So this is important for the SYK model, as I'm going to discuss in a bit. And then there's the usual holographic counter term S of x, where S is a function related to the superpotential. So it's e to the minus q times w, where q is the integral of this kinetic function, and w is this bizarre looking combination of v and u. So what's the meaning of this? Well, q is essentially the conformal factor. So it's a quantity that changes if you do dilaton-dependent while rescalings of the metric. And you can change u in this way to any function you like, including 0. And w stands for while, is a combination of potentials that is while invariant. So if you do any dilaton-dependent while rescaling, this function remains invariant. And with these boundary terms, you have a well-defined variational principle. So the first variation of the action vanishes for all variations that preserve your boundary conditions. And of course, the theory requires the specification of precise boundary conditions on metric and dilaton, which I'm going to elaborate on the next slide. And just in case you didn't know, so from work in the 90s, it became clear that all solutions of all dilaton gravity models can be obtained in closed form, and they're known globally for all models. Okay, so the second order formulation is very useful for building our intuition and for guessing physically reasonable boundary conditions. But for many technical applications, the first order formulation is technically a bit superior, at least very useful. So let me introduce this in the absence of boundaries. So if you're familiar with the Chern-Simons formulation of 3D gravity, you can think about this formulation as the two-dimensional analog. So the two-dimensional version is this Poisson-Sigma model action. And the Poisson-Sigma model is specified by a set of target space coordinates of a Poisson manifold, xi, by a connection one form ai, by some coupling constant, like the Chern-Simons level. It's essentially inverse Newton's constant. And the most important input is in this Poisson tensor Pij, which is antisymmetric and obeys this nonlinear Jacobi identity. And as a consequence of these properties, this model exhibits a gauge invariance that is in general nonlinear. So let's focus on the second line here. You can see that if the Poisson tensor was constant, you had abelian gauge symmetries. If the Poisson tensor is linear in the target space coordinates, you have a standard Yang-Mills type of gauge symmetries, where these are then the structure constants of your Lie algebra. But if the Poisson tensor is nonlinear, you have some nonlinear generalization of Lie algebra, so you have nonlinear gauge symmetries. And this formulation was introduced by Ikeda and independently Schall and Strobel in the mid-90s. So in the same way that Chern-Simons theory is not identical to gravity, but only if you further specify what you identify as your dry-bind, also Poisson-Sigma models are not generically gravity. You have to specify how to translate to the Cartan formulation. So let's do this now. One input is the spin connection, and two dimension is unique because you can dualize the spin connection to something that has no Lorentz indices. So that's one entry in the connection. And the other two entries are the Zweibein. And the target space coordinates contain the dilaton x. So x is the same as in the second order formulation. And then additional scalar fields that you can think of as Lagrange multipliers for torsion constraints. And just a minor technical note, I often use light cone coordinates because they are useful in two dimensions. So plus minus refers to this light cone gauge of the Minkowski space metric. Okay, and in order to get a gravity theory, you have to choose the Poisson tensor in this way. So part of this Poisson tensor is linear in the target space coordinate, and that comes about because there's always local Lorentz transformations, which is Lie algebra, namely SO1, 1. And then there's one entry in the Poisson tensor that in general is nonlinear. So in general, you do have nonlinear gauge symmetries depending on the choices of u and v. And u and v are the same functions, u and v, that are introduced in the second order formulation. So u is the kinetic potential and v the dilaton self-interaction potential. So only for a few models like Chakif-Teitelbaum, where u is 0 and v is linear, you do get Lie algebra symmetries. Otherwise, you have something more general. Now, I haven't written down the lower triangular part because the Poisson tensor is antisymmetric. And as another consequence of antisymmetry, the rank of the Poisson tensor has to be even. But since its dimension is odd, also the dimension of the kernel has to be odd. So there's either a one-dimensional or a three-dimensional kernel in the Poisson tensor. And that has a profound physical consequence, namely the universal existence of a conserved Casimir function, which I've written down here explicitly in terms of these functions q and the while invariant function w. And on shell, this is totally conserved. So by this, I mean that space and time derivative of this quantity c vanish on shell, and it's related to the black hole mass. So from this algebraic statement, you can deduce that all dilaton gravity models have to have a conserved quantity that when you have black holes, you can interpret as a black hole mass. Okay, so this is my last slide on 2D gravity, but it's going to be very busy. So here I want to discuss some things you can do with two-dimensional dilaton gravity. So let's start with classical solutions. There are two different sectors, constant and linear dilaton sector. The constant dilaton vector are non-generic. They are those solutions where the rank of the Poisson tensor is 0 on shell. So that requires dilaton to be constant and to solve the equation that v of x is equal to 0. CdV just means constant dilaton vacuum. And obviously not all models allow for such solutions. So for instance, the Schwarzschild black hole or the CGHS model have a v that is constant but non-zero. So therefore this equation is no solution and there are no constant dilaton vacuum. Whenever you do have such solutions, it turns out that the metric always has to be maximally symmetric. So it's either de Sitter, anti-de Sitter, or flat locally. And this sector led to early attempts of EDS2 holography, but has the feature or the issue that you can't have finite energy excitations. And I'm not going to focus on this sector in the rest of my talk. So instead, I'm going to focus on the generic sector, the linear dilaton vacuum. They are defined by the property that the rank of the Poisson tensor is 2 on shell. And in that case, the dilaton depends on one of the coordinates. You can use it as a radial coordinate, and it's often useful to rescale it in this way. So r is now my actual radial coordinate. And in terms of this coordinate r and an identification time, retarded or advanced time u, the metric can be presented in this simple form. So this is the solution in an Eddington-Finkelstein patch for all two-dimensional dilaton gravity models expressed again in terms of these functions q, w, and the Casimir c. So what you can read off from this is a generalized Birkhoff theorem. All solutions of all models have a killing vector, which is du in these coordinates. So one issue of this sector, and perhaps the reason why it was not used initially to do holography, is that it's not obvious how to do EDS2 holography, because the dilaton apparently breaks all the isometries, or at least most of them. du is maintained, but all others are broken. So why is this? Well, in the linear dilaton sector, when you act with the Lie derivative along any vector field on the dilaton, you get something that in general is non-zero. So if you have your favorite boundary conditions that leads to some asymptotic isometries, for instance, in ADS2, then chances are that the dilaton is going to break almost all of them. So you're losing all the asymptotic symmetries. So in order to decide whether or not this really happens, whether the dilaton breaks the isometries, we have to discuss boundary conditions. So this is my next point. There are again two different choices you can make, fixed versus fluctuating dilaton at the boundary. So let me describe pictorially what I mean by these two cases. Fixed dilaton means that the variation of the dilaton is small as compared to the value of the dilaton at the boundary. So in other words, delta x divided by x goes to 0 as you approach the boundary. So the boundary is a dilaton isosurface. So in the ADS2 case, that means you have concentric circles in this Poincare disk. Now, for a long time, this seemed obviously the right choice. So why was it sort of obvious? Well, you can interpret the dilaton as a space-time dependent inverse Newton's constant, and it seemed appropriate that the Newton constant should not fluctuate asymptotically at the asymptotic boundary, because you would expect there, classical physics to kick in. So this was the choice that was mostly made, but there is an alternative, namely fluctuating dilaton boundary conditions. And they're more general because now you allow the dilaton to fluctuate to leading order. So delta x divided by x is something of order of unity at the boundary. And that means the boundary no longer has to be a dilaton isosurface. It can be some curve shaped like this black curve here. Now, this is not obviously the right choice, but it has a number of nice features. Sorry. So first of all, it can be made compatible with a variational principle, which is not completely obvious. It also resolves the issue with breaking of asymptotic isometries, because now you no longer care that the Lie variation of the dilaton doesn't give 0, because the boundary conditions allow the dilaton to fluctuate to leading order. And this set of boundary conditions is actually required for the Chakif-Teitelbaum-Sachs-Kitaev correspondence. So that's another reason why it's popular. And in fact, it leads a whole menagerie of possibilities for boundary conditions for the metric. Also, it generalizes naturally to higher spin theories, but I'm not going to discuss them in my talk today. Okay, so let's assume now that you have picked your favorite bulk action, your favorite dilaton gravity model, and you have equipped it with your favorite set of boundary conditions. What can you do next? So what are some of the observers that you can discuss? Well, you can certainly discuss thermodynamical observers. So there's black hole thermodynamics to consider. You get the free energy from the Euclidean on-shell action in a straightforward fashion. In this case, I'm again restricting myself to fixed dilaton at the boundary. So xc denotes the value of the dilaton at the cutoff surface, and the free energy then depends on the temperature and the dilaton evaluated at this cutoff surface. And it's just given by temperature times the on-shell action. Now, let me spare you most of the details. Let me just state that there's a slew of possibilities. You can do sort of chemistry. You got numerous possibilities for specific heat, dilaton chemical potential, etc. Here, I just show as a class of examples this AB family of models. So A is a parameter that gives you the proportionality to 1 over the dilaton in the kinetic potential, and B gives you the power of the monomial in the dilaton self-interaction potential. And you can see that thermodynamics does pose some constraints on the model space, so it allows you to exclude some models. So if you want to have positive temperature, you have to be above this line B minus 1. If you want to exclude solutions that are asymptotically singular, so by asymptotically I mean at large values of the dilaton, then you have to exclude the orange region. And if you want to have positive pressure or positive dilaton chemical potential, then you have to exclude the green regions. So you end up with this white triangle region. If you additionally want positive specific heat, you end up only with this upper part. And interestingly, the most prominent models all lie on the boundary of this triangle. So the Chakif-Teitelbaum model is here at this intersection. The Witten black hole is at this intersection. Schwarzschild black hole is at this boundary. Minkowski-Groundstedt models, so Schwarzschild-Tangalini are this dotted line, and ADS-Groundstedt models are this dashed line. And Rindler-Groundstedt models would be these models, and models without kinetic term would be this line here. You can also derive a universal result for entropy. So the entropy is just given by the dilaton evaluated at the horizon times the value of the coupling constant. And in some cases, you can do some cardiology. So you can do a sort of microstate counting. And final application that I want to mention is that quasi-local thermodynamics leads to a flow equation. So this was studied by David Gross, Edgar Shagulian, and collaborators a year ago. So they were considering deformation of quantum mechanics. So gamma c is again the action evaluated on some cutoff surface, and lambda tells you how you change the cutoff. So lambda is essentially xc. And they consider the class of deformations that is interpretable as a dimensional reduced TT bar deformation. So these are some thermodynamical applications. Let me now come to one of the main stories of excitement of the past years, the Chakif-Teitelbaum-Sachs-Kitaev correspondence and the chaos bound. So naturally, I won't give a fully fledged introduction. So let me just say about the condensed metasite that the Sachs-Kitaev model is a strongly interacting quantum system that is solvable at large n, where n is the number of fermions, and they're subject to some random self-interactions that you draw from some Gaussian ensemble, and it's characterized by coupling strength J. Now, a key observation that was made first in talks by Kitaev at KITP is that the effective action governing the collective low temperature modes is given by this Schwarzian action. So the Schwarzian action depends functionally on the time reparameterization field H. And the Lagrangian is governed by this Schwarzian bracket here, defined here. So this is the Schwarzian derivative, the unique operator that annihilates all the SL2R transformations, but nothing else. And n is the number of fermions and j is the coupling strength. So what you can see is an emergent reparameterization invariance in this limit. And this is indicative of gravity-like behavior. So this was a first good hint that maybe there's a gravity dual. This was worked out in great detail in this work by Maldacena and Stanford in 2016. So they calculated the Lyapunov exponent at strong coupling and found that it's given by 2 pi times temperature times correction terms that vanish in the infinite J limit. So in the infinite J limit, this actually saturates the chaos bound. So this is again an indication for gravity-like behavior. And in some follow-up work with Young, they proposed as the dual gravity theory that you give Teitelbaum model with fluctuating dilaton boundary conditions. Okay, so there are numerous others applications or ideas that you can implement and study in two-dimensional gravity. I'll just go briefly through the list, but I'm not going to explain this in more detail. I'll have to say more about flat space holography in 3 dimensions. So let me just flash this here briefly for viewers on YouTube, and you can go to the various links if you're interested in these topics. Also, there was a lot of excitement in the past year, or a bit more than a year. A new spin on understanding the information loss problem. So this is the famous island proposal. And, you know, there was a number of concepts that was introduced to tackle with information loss problems. So there's a number of vocabulary that I've summarized here that goes back all the way to the 80s. And the most recent addition are these islands that allow a nice application of this quantum extremal surfaces introduced by Engelhard and Wall. But now the new twist in the story is that you allow island regions in the black hole region. So the main idea is that the fine-grained entropy of Hawking radiation that is compatible with unitarity and with the page curve is given by these quantum extremal surfaces, where the phenomena entropy is now calculated not just for a surface in the outside that contains Hawking radiation, but you can also have islands in the black hole interior, and that can lead to consistency with the page curve. And we've heard some talks in this conference about this. So the main point I want to make here is that information loss exists in any dimensions. You can study it in particular in low dimension models and in, specifically in 2 dimensions. And this was done to make progress on implementing these interesting ideas. Okay, so this is the last point that I just flash here. Let me not even address it. So this is just for YouTube viewers. And also this whole discussion here, I'll just flash it in case someone wants to discuss it. By the way, it's not just for YouTube viewers. In case you're interested in any of these issues, I'm happy to discuss it in the Slack channel afterwards. So let me conclude at this point the 2-dimensional discussion by stating that 2 dimensions provides a plethora of toy models for classical and quantum gravity. And, you know, one often used slogan is that you can use these 2-dimensional models you can view them as hydrogen atom of quantum gravity, in the sense that the 2-dimensional models of quantum gravity could be as useful for understanding of quantum gravity as the hydrogen atom was for the understanding of quantum mechanics. Okay, so this concludes my 2-dimensional part, and now I'm going to move on to 3 dimensions. So in 3 dimensions, I'm going to ask the same 4 questions. Let me start with why. Well, 3 is the lowest dimension where you have Einstein gravity. It's also the lowest dimension where the boundary can be a space-time, where the horizon can have a structure, and where metrics need not be conformally flat. These are all features that are shared with higher dimensional gravity. Also, 3 is the lowest dimension where the transverse traces part of metric fluctuations can exist. So if you decompose your fluctuations into a transverse traceless piece, a gauge part, and a trace part, you see that in 3 dimensions you have 2 TT parts, TT modes, at least off-shell. And on-shell, they can either be boundary gravitons, like in Einstein gravity, where you don't have any local on-shell excitations, or they can turn into massive spin-2 helicities in massive gravity theories. And finally, it is 3 factors, again, ubiquitous in string compactifications. And there was a lot of interesting progress in recent years in strings on ADS3 cross S3 times some K3 manifold, or on ADS3 times S3 times S3 times S1. So again, 3D gravity is simple, but not too simple for black holes and holography. And for some purposes, despite of being closer to higher dimensional gravity, it's even simpler than 2 dimensions. Okay, so which gravity theory should we consider? Well, this slide is going to be much shorter than the 2-dimensional counterpart. In this talk, I'm going to exclusively discuss 3D Einstein gravity. There are various massive gravity theories, but Einstein gravity is already interesting enough, so let's focus on that. Okay, so how should we formulate 3D gravity? Again, there are at least 2 different formulations, second and first order. So again, I'll be a bit shorter than in 2 dimensions. What I want to highlight here is that the implementation of boundary conditions is crucial. So there's this seminal work by Brown and No, who showed that ADS3 Einstein gravity, if it exists, must be dual to a 2-dimensional conformal field theory, in the sense that the physical phase space, or in the quantum theory, the Hilbert space, falls into representations of the 2-dimensional conformal algebra, so 2 copies of the Virasoro algebra, and they calculated the value of the central charge. So the Brown and No central charge is given by 3L over 2G, where L is the ADS radius and G is Newton's coupling constant. And they derived this from an analysis of the asymptotic symmetry algebra. So what is this? The asymptotic symmetry algebra consists of all boundary condition preserving transformations modulo pure gauge transformations. So in case you're not familiar with these concepts, an important consequence of the Brown and No analysis is that the diffeomorphisms fall into 2 classes. Those that are proper, so they're pure gauge even in the presence of boundaries, and those that are non-proper, so those are the ones that constitute the asymptotic symmetries, and they're non-trivial on the boundary. And these non-proper diffeomorphisms generate edge states, also known as boundary gravitons. So they generate physical states. Now, all of the above also applies to the first order Orchard-Simons formulation. So let me not repeat the statements. I'm just going to write down the first order action. So this is a standard Chern-Simons action. In this case, it's a difference of 2 Chern-Simons actions. And the bulk input is the choice of the gauge group. So if you want ADS3 gravity, the gauge connections A plus minus have to belong to SL2R. We also have to specify the relation to Cartan variables. So the gauge connection is a linear combination of dualized spin connection and dry-bind. So again, we're exploiting a feature that is unique to this specific dimension. So only in 3 dimension is it true that the dualized spin connection has the same index structure as the dry-bind. And finally, we have to specify the coupling constant, which in this case is the Chern-Simons level, and it's essentially 1 over Newton's constant. Okay, so what can we do in 3-dimensional gravity? So let me highlight a couple of topics here. So this is again the last slide, but again, it's kind of busy, and I'm not going to discuss all the topics here in great detail. So let's start with this menagerie of ADS3 boundary conditions. So more than a quarter of a century of the discovery by Brown and No, there was a sort of Cambrian explosion of boundary conditions, starting with this work by Comperson and Strominger. So they took ADS3 Einstein gravity, but implemented boundary conditions that differed from the Brown and No boundary conditions. And I don't want to go through this whole zoo of possibilities. Let me just explain what the red numbers in parentheses means. So these 2 here for Brown and No means that you have 2 towers of boundary charges. So there's a tower of left moving boundary gravitons and the tower of right moving boundary gravitons. And as you can see, depending on the boundary conditions, this number may change. So in some cases you have, like in the Brown and No case, 2 towers of charges, but in some cases you have 4. So by 2016, it became clear that it would be nice to put some order into this zoo, and also to find out what is actually the largest number that is possible. Is it 4 or is it some higher number? And if so, what is it? And this was done in this work together with one of my former PhD students, Max Regler, who is currently in Harvard. Well, he's not physically in Harvard because there's lockdown, and applying for positions now. So what we found is that the most general set of boundary conditions allows for 6 towers of charges and leads to 2 SL2 current algebras as asymptotic symmetries. And all other cases discussed above are either special cases or the formations of special cases. And all of this follows from boundary conditions summarized here. So if you're familiar with the Chern-Simons formulation and how to impose boundary conditions, you will have seen this probably. If you're not familiar with this, then let me just focus on the second line here. So the essential information about state-dependent functions is captured by these 3 variations. And the reason why there are 3 functions appearing here is because we're in SL2. So there are 3 SL2 generators, L plus, L0, and L minus. And if you switch all of them on, then you are in the most general case. And since we have two SL2s, we have 3 plus 3, so this equals to 6 towers of charges. If you want to obtain Brown-Renault, for instance, then you have to set to 0 this part here and this part, so you keep only the highest weight part. And if you want, as another example, the Heisenberg boundary conditions, you switch off the highest weight and the lowest weight part and only keep the Cartan subalgebra part. So in this way, you can recover all these previous boundary conditions as special cases or deformations. And in some sense, this could have been anticipated from very old and very nice paper by Elitzer, Moore, Schwimmer, and Seiberg from the late 90s. And the slogan you can take away from this is that the loosest set of boundary conditions always has the loop algebra of the gauge algebra as a asymptotic symmetry algebra. So SL2 current algebra is the loop algebra of SL2. And this slogan can be applied also to higher spin theories where the same statement is true. Okay, so the last topic I want to discuss in some detail is flat space holography. So it can be formulated as a rather provocative research agenda. So take the lambda to 0 limit of the 16,000 ADS CFT papers. That's maybe not the best way of phrasing this research subject, because there are at least two classes of problems. So there are technical problems. This limit may not always be straightforward, and in some cases it may not even exist. And there's also a conceptual problem. So why should it be true in the first place that you can get flat space holography from ADS holography by sending the cosmology constant to 0? Flat space is not just the lambda to 0 limit of ADS, it's also the lambda to 0 limit of the sitter. So maybe we should instead do the lambda to 0 limit of the sitter holography. But if you look at the current implementation of the sitter holography and on ADS CFT, they are conceptually and also technically rather different. So it's not clear how flat space holography could incorporate both these limits simultaneously. So maybe it does neither. So often the best resolution is just to ignore limits and work directly in flat space without taking any limit from until the sitter or the sitter. So let me guide you through some of the milestones. So this list is by no means complete, but well, I had to do some selection. So the analog of the Brown-Renault analysis, so the implementation of precise boundary conditions and the asymptotic symmetry analysis, including the calculation of the central extension, that was done by Barnich and Compare in 2006. And they found that the asymptotic symmetry algebra is the BMS3 algebra. So the same algebra that featured in Andrea's talk before, but in one dimension lower. And in 3 dimension, it does have a central extension. So the LNs are what some people call super rotations, so they generate diff S1. So for Einstein gravity, there's no central extension here. Otherwise, it would be one copy of the Virasoro algebra. Then the M's, they all commute with each other. So this is what is called super translations. And the commutator between super rotation and super translations gives something on the right-hand side that looks like a Virasoro algebra for the super translations. And here you do have a non-trivial central extension in Einstein gravity. And in independent work, Arjun Bakshi and Rajesh Gopakuma were investigating Galilean conformal algebras. And Arjun realized that Galilean conformal algebras are isomorphic to BMS3. So this is algebraically true. It's conceptually maybe a bit misleading because you should rather view BMS3 as a Carolian conformal algebra, but in 2 dimensions, there's no difference between taking the Galilean and the Carolian or ultra-relativistic limit. Okay, so one nice aspect of flat space Einstein gravity in 3 dimension is that even though the solutions are locally trivial, so your Einstein equation is just R min equal to 0, and since in 3 dimensions the Ritchie tensor determines the Riemann tensor, also the Riemann tensor is trivial locally. But globally, solutions can be non-trivial, essentially for the same reason as in ADS3. So you can get non-trivial orbifolds of flat space, and some of them have interpretation as thermal states, and they are known as flat space cosmologies. And these boundary conditions, together with this observation, has led to a concrete model or proposal for flat space holography known as flat space chirogravity. Okay, so let me now address some rudimentary checks of flat space holography. So they're all based on, or essentially based on the symmetries. So from an ADS CFT perspective, you could argue they're kind of trivial, but as opposed to ADS CFT, we don't have the luxury of having all the field theory results available. So when ADS CFT came along, we could use a lot of the seminal work on CFTs in 2 dimensions that were discovered in the 80s and 90s. Now, in this flat space holographic correspondence in 3 dimensions, we often have to invent or construct the field theory results as we go along. So therefore, it's important to even do these most rudimentary checks. So one of them is to derive a Cardi-like formula for flat space cosmologies. So you can derive this in the same spirit as the Cardi formula. So from an analog of modular S transformation and exploiting a gap between excited states and the global vacuum. And you end up with a formula for the entropy that is reminiscent of the Cardi formula, but differs in detail. And it agrees with the macroscopic Bekenstein-Hawking entropy. And this is one of the results that actually you can obtain as a lambda to 0 limit from the usual Cardi formula. Okay, so another interesting check is the holographic computation of correlation function, in particular of stress tensor correlators. So we would like to know if this cornerstone of the holographic dictionary, so the GKPW relation between CFT correlation functions and corresponding gravity quantities, if this also applies to flat space. And the answer is yes, at least for these stress tensor correlators. So in GCAs and also the Carolean counterparts, you can prove recursion relations between endpoint functions of the Galilean analog of the stress tensor that are reminiscent of the Belavin-Polyakov-Samologikov recursion relations. And by doing some extra work, you can prove the same recursion relations on the gravity side. And then you can explicitly calculate the 2-point function so that you have one starting point for your complete induction proof. So with this, you can show that all the endpoint correlation functions match, and the GKPW dictionary works at least for this class of correlation functions. So the final check I want to highlight here is entanglement entropy and its holographic counterpart. So again, it's something that we had to first reinvent on the field theory side by following work from the 90s by Holze, Wilczek, and Larsen, and Kadi Calabrese in the O's. So it turns out that the entanglement entropy in Galilean and Carolean conformal field theories takes a form that is slightly different from that in normal relativistic CFTs. So you have one piece that looks like in a chiral CFT, and that is only there if the Virasoro central charge is non-zero. So for Einstein gravity or the field theory dual to Einstein gravity, this part is actually not there. And then there's a part that is Lorentz non-invariant, and that depends on both the temporal and the spatial extent of your entangling region. So this is qualitatively different from what you get in a standard CFT2. And it can be shown that you can obtain the same result also on the gravity side, either through a Wilson line type of calculation or using a special geodesic construction. So also this part of the holographic dictionary appears to work. Now there's much more, but since I think my time will be soon over, let me not go into these interesting recent developments on BMS3, conformal blocks, and bootstrap, but start to wrap up. So I also am going to skip these developments on quantum energy conditions. Again, if you have questions on any of these topics, please just contact me in the Slack channel or send me an email. So the same applies to this story of Near Horizon software. So I'm very sorry that I display this only for YouTube viewers, but there's just not enough time to address this, and I didn't want to give a shallow introduction to this. There's too much to say. This would be a full 1 hour talk. So if you're interested in this, you can just click on this link and then you get a 1 hour talk actually. And also strings on ADS3, let me just again flash this recent literature. And if you're interested in these developments, I recommend to look at these recent papers by Lorenz Eberhard, Matthias Gabardel, and collaborators. So let me conclude here with a similar statement. 3-dimensional gravity provides one toy model, so not a plethora of toy models, but one very interesting toy model, namely Einstein gravity, for classical and quantum gravity. And you can use here the same slogan. It's kind of the hydrogen atom of quantum gravity. So let me conclude with an outlook. So the long-term question that many of us are trying to address is how general is holography? And I think it's a question that is worthwhile to address from various angles. And many of the issues that appear here, like the information loss problem, for instance, are of conceptual nature, So their resolution shouldn't depend on the dimension, but the techniques that we can use, of course, do depend on the dimension. So the main philosophy is to use this sound strategy to address these issues in lower dimensional gravity. But of course, eventually, an interesting prospect and an interesting task is to lift some of the results that we've obtained to higher dimensions. So let me stop here. Thank you for your attention, and I hope to see you at Strings 2022 in Vienna when the pandemic hopefully is over. Thanks.
So thank you, Daniel, for a very nice overall review. I guess we have about 15 minutes or so for questions and discussions. So the floor is open. Anyone wants to ask a question, please go ahead.
I don't hear anything.
Hello,
So
Daniel, can you hear me?
The thing that I have anticipated has not happened again. So maybe I log out and log in again, because I can't hear anything at the moment. Okay, so let me just log out briefly.
You should first stop sharing.
So how do I log out if I'm the host?
Can you hear now, or? Well, I guess you can't.
You can just simply leave. You don't have to log out, Daniel. You can
Yeah,
simply
I don't
leave.
hear anything still. So
okay, so let me write to you. Right. Yes. Okay.
Hi, Ian. I'm just going to get a glass of water. I'll be back in 2 minutes.
Sure. Yeah, we still have the question and answer session with Daniel, though. Yeah, so you can take your time. Don't worry.
Yeah, sorry.
While we are waiting for Daniel to log back in, if anybody has a question, can already start typing it in the chat box, so we can sort of have it ready.
Can you hear me now?
Hello?
Yeah, Daniel, you are back, but we can hear you very faintly. Can you hear us? Maybe we should write.
Yes.
Okay. But we can hear you only very faintly.
Okay. I'm sorry for that.
No, that's getting better, actually.
Oh, now it's getting okay.
Yeah, I apologize for these technical difficulties.
No, I think it's perfect now.
Okay.
So yes, so questions and comments for Daniel. Well, if there are no questions for Daniel, then so I can ask a couple of very quick questions.
Sure.
So it may be very naive, actually, but I'm just curious that this flat space holography that you're talking about, is it possible to know or see easily whether the dual field theory should be strongly coupled, or it should be a local description, or questions of this sort? Can it be simply understood, or?
Yeah, so there's a similar UV-IR correspondence as in ADS in the following sense. So in ADS3 CFT2, if you go to the limit where Newton's constant is very small, you get a very large central charge. So you have a large number of degrees of freedom. And precisely the same thing happens in flat space holography. So the Cardy formula again contains the central charge Cm that I mentioned. And the central charge is again inversely proportional to the Newton constant. So if you go to the semi-classic limit where Newton's constant goes to 0, the number of states increases. So you have again the same feature as in ADS3 CFT2. Yeah, so that aspect is the same. But of course we know far less about this Carolean or Galilean conformal field theories than we know about ordinary CFTs. So many of the questions that people ask now about two-dimensional conformal field theories are not questions that we can yet address in this Galilean conformal field theory. So we are still doing our homework in establishing the bootstrap program and other results that have been known in the CFT2 context already in the 80s. But we will get there, I guess, in the near future at some point.
But you expect that this is still a strongly coupled?
I do expect this, yes. That's my expectation, yes.
And also there's some sort of a local description. Or that's not necessary.
Yeah, it's perhaps, well, I expect so. It may be a bit less clear if you have a Lorentz non-invariant field theory, what precisely you mean by local. I mean, you don't have Lorentz invariance to start with. But yeah, I do expect the two-dimensional field theory to be a local Galilean, or rather Carolean conformal field theory in this in this flat space three-dimensional correspondence.
I see. And the other naive question I had in mind was sort of related to the first part of your talk, where you're
right.
basically saying that, you know, so this boundary condition on the dilaton that people used to impose, it has to
yes.
fall off near the boundary. That actually destroys many of the symmetries that you would otherwise have. So once you allow
right.
sort of relaxing that condition, then you get back the asymptotic symmetries, etc. I'm just curious, in higher dimensions, for example, if I have fields which are growing towards the boundary, of course, I mean, that's a bad thing. I mean, that's not necessarily bad, but that's more complicated because then you have back reaction and so on and so forth to
right.
take care of.
Right.
But I'm curious whether by having or by allowing such boundary conditions, can you actually find new asymptotic symmetries in higher dimensions?
This is a fantastic question. I think it's the right question to ask. And I think the answer is yes. And we see already some indications that this is so. I think this is precisely the type of question that the community should be asking now. So I think this is possible for sure. And I think it's one of the right research directions to pursue now. So to generalize the usual asymptotic ADS boundary conditions to go beyond the usual Pfefferman-Gram expansions also in higher dimensions. There are indications that this is possible and that you can get new asymptotic symmetries beyond the conformal symmetries that we are familiar with. And that can, put a new perspective on holography and perhaps lead to developments either reminiscent of SYK-HAT correspondence or to, a better and more comprehensive understanding of what is possible in the first place and what does it mean to allow this looser set of boundary conditions and how are various sets of boundary conditions interrelated. And also, is there sort of a loosest or most general set of boundary conditions that is still consistent with all your consistency requirements? Although it may not be obvious what are the consistency requirements that we have to impose, because, as a function of time, more and more of requirements that we thought would be sacred have been relaxed. So canonical boundary charges initially were assumed to be integrable, conserved, and finite. But in the past decade, we've seen examples where canonical boundary charges are either not conserved or not integrable in field space, and even examples where they're not even finite, but still convey interesting information, like in some of these subleading soft theorems and generalizations to magnetic versions of charges. So I think this is a very interesting research agenda, and I don't think the community has gone to the bottom of this. So I think this is something we should investigate. Yes.
Thanks. So I think we still have a few minutes left. So
can I ask one question to Daniel?
Sure.
So this is related to BMS. So as we know that in 3 dimension near the horizon, we recover BMS3, which has the algebra has 2 sets of Virasoro kind of thing. So do we get something like that in 2 dimension?
Yeah. So this is in the part that I, sorry, that I essentially skipped. So there are different ways to implement near horizon boundary conditions. And depending on what you do precisely, you can get different symmetries. So it is true that you can get BMS3 also in the near horizon theory. From my perspective, a more natural result is that you get two U1 current algebras. And you can view all other boundary conditions as composites in terms of this fundamental building block. Okay, the short answer is yes, you can get BMS3, but I'm not sure it's necessarily the simplest way of representing near horizon boundary conditions and near horizon state. So in my view, a slightly simpler way of representing near horizon excitations is in terms of U1 current algebras, which is what I called Heisenberg boundary conditions.
And I mean, can we have any kind of soft theorem into?
Yes, indeed. So when you implement these near horizon boundary conditions, you do get soft excitation. So this is something you can actually show. So what do I mean by this? Well, you can construct a Hamiltonian, which is the generator of near horizon time translations. And you can check that the Hamiltonian commutes with all the descendants, with all the generators of your near horizon symmetry algebra. So this is quite different, of course, from Virasoro, where L0 does not commute with the Virasoro generators. But here the Hamiltonian commutes with the whole algebra. So that means all descendants, all near horizon descendants of any state have the same energy as the original state. And that means that the excitations, by definition, are soft in the sense of having vanishing energy. And this is generic. This is true both for these BMS-like boundary conditions and for the Heisenberg boundary conditions.
Okay, thanks.
Sure.
Any more questions or comments? If not, then let's thank Daniel for this wonderful review. And of course, please continue your discussions in the Slack. But now we have to shift to the third and last talk of this session. I request Sean to share his screen.
Yeah, 1 minute.
Sure. Yes, perfect. Great. So we are right on time. So without any further delay, let's begin. So we are delighted to have Sean Hartnoll from Stanford telling us about the classical interior of black holes in holography. So over to you, Sean.
Great. Thank you, organizers. It's a pleasure to be talking at this conference. Indeed, so I'm going to talk a bit about the inside of black holes, but classically. And so what I'm going to say is going to be based on a series of 3 papers with various collaborators. And so the first one was with Arik Frenkel, who's a graduate student at Stanford, Joret, who's a postdoc at Stanford, and Darius, who was an undergrad and is just starting at MIT now. And then later we had the good fortune to be joined by Gary Horowitz and George Santos. So let me start with a few general comments about the classical black holes exteriors and interiors. So first, as I'm sure you all know, in holography, an eternal black hole is dual to the thermophile double state of a CFT, right? So in particular, there are 2 boundaries of the black hole, and these describe the 2 entangled thermal copies of the CFT. Now, the exterior of the black hole, okay, so these are typically classically stable, meaning if you perturb something outside the black, if you drop a pin outside the black hole, some ripples fall through the horizon, some stuff radiates off to infinity, and the black hole goes back to where it was. And so the exterior black holes are stable. And if they're not stable, then it just means they go to some other black hole that is stable. Okay, so if you found the right black hole, it's stable outside. And it's very well understood by now that the exterior classical dynamics, meaning stuff falling into the black hole, dually describes the approach to thermal equilibrium of the dual quantum field theory. And this is described by, for example, quasi-normal modes that describe the ring down to equilibrium. And among those quasi-normal modes are special ones that can describe things like hydrodynamics, like sound waves and diffusion and so on. And so the outside is I think, pretty well understood. And yeah, it describes the approach to thermal equilibrium. Okay, now inside the black hole is a completely different situation, because black hole interiors are essentially certainly all your favorite ones, are classically unstable. There's an extremely rich interior dynamics, and it's not surprising that they're unstable, right? Because they're crunching towards some singularity. And so the rich dynamics of black hole interiors are widely studied by mathematicians, going at least back to Penrose. But I think it's fair to say that despite this very rich structure, the holographic or quantum gravity implications of this rich results have not really been explored at all. Now, why should we? And for good reason, that maybe we haven't, firstly, maybe we haven't cared too much about what happens inside the black hole. And secondly, even if we were interested, it's not clear how to probe it. Okay, but recently a few things, there's been a lot of interest in the inside of black holes. I think some of the more robust things that one can say is that the interior evolution probably has something more refined to say about the approach to thermal equilibrium than we can see on the outside. On the outside, we just see everything decay. You can have some thermalization time, right, which is the time to decay, but the inside keeps evolving, as Susskind has been emphasizing for a few years now. And so it seems likely that it's possible that the inside interior evolution of the black hole tells us something a bit more fine-grained about the dual many-body approach to equilibrium. And if that's true, then these instabilities of the interior are something that we probably want to understand. And so perhaps the cleanest example of this is this Hartnoll-Maldacena result that shows that the entanglement entropy at late time, a certain entanglement entropy, is sensitive to things behind the horizon. Okay, and in addition to that, I think it's obvious, or seems very likely, that if you want to understand deep quantum gravity questions like what happens to an infalling observer, you'd better understand what happens classically to an infalling observer before trying to solve the quantum problem. Okay, so this is meant to be motivation for thinking about the classical dynamics of the black hole interior. So today, this is a plan. I want to make a few small steps towards more generic interiors. Okay, so just not Schwarzschild, for example. Now, a truly generic interior is going to be highly inhomogeneous. Different points in space are going to decouple close to singularity, and it's going to be extremely complicated. So we're going to take a step in the direction of genericity, but we will retain spatial homogeneity, which means everything's still just ODEs. Okay, but nonetheless, this is a step in the right direction, and it's going to have the advantage of being both tractable and holographically motivated. And so we're going to consider three different setups. I'm going to start with, and actually these correspond to the three papers that I mentioned, and talk about neutral black holes, charged black holes, and then finally charged black holes with charged matter. Okay. All right, so let's start with neutral black holes. So that was this first paper. Okay, and so here's how we're going to think about it. Okay, so once again, let me come back to the idea is that, let's say Schwarzschild ADS is a very reasonable thing to consider on the outside because it's stable. However, the interior of Schwarzschild ADS is unstable. And so if you want to think about the interior, you probably shouldn't be too fixated by the interior of Schwarzschild ADS. Let's try to deform it to something more general. So how do we do that? We have to start outside. So one thing we can do is, so I want to say that the Schwarzschild singularity is not generic, but a CFT is also not generic. You can typically deform it by a relevant operator. So a natural setup to consider is I'm going to deform the boundary CFT by a relevant operator, and that will trigger an RG flow. Okay, and so let's think of Schwarzschild. So here's our Penrose diagram, and so instability means evolution in time in the interior. But one way to source that is with just a time-independent source on the boundary. That will induce some RG flow as we go in. Okay, but as we go past the horizon, that RG flow becomes time evolution. Right, so an RG flow in the exterior is one way to source the time-dependent instability in the interior, and it's a very simple one and are pretty well motivated, I would say. So we deform the CFT by some operator on the boundary, uniform in space and time. But we're at non-zero temperature, right? Because we have the black hole. And so we're going to have the RG flow, things become radially dependent. But what we can do is the RG flow, the radial dependence doesn't stop at the horizon, it just keeps going. So we just keep evolving the space-time in past the horizon. Okay, so we're going to continue the holographic normalization group flow past the horizon. In the interior, the flow corresponds to a time evolution, right? Because the radial coordinate becomes time in the black hole interior. Right, so I think of this as sort of a generalized RG flow, right? We start at z equals 0, which is the boundary, z is some coordinate. We flow all the way to z equals the horizon, that's the far infrared. And then we just keep going. And so we go to z equals infinity, and I don't know what to call that. Let's call that the trans-infrared. And that's the singularity up here. Okay? And what we're going to see is that this flow develops certain scaling properties towards a singularity, which has the flavor of some kind of fixed point. Okay, that's the plan. So let me just draw that picture again. And so the main lesson is going to be that we have a more generic quantum field theory, meaning that we deform the CFT by some relevant operator. That will trigger some flow, right? So remember, an operator, the source for the operator is a boundary value for the field here. That deforms ADS-Schwarzschild, you carry it through. And here we're going to find that we have what's called a Kasner universe. And there's going to be a certain scaling exponent, PT. And PT, the scaling exponent near the singularity, is going to depend on the deformation. All right. And so this gives us a one parameter deformation away from Schwarzschild. And so it's correct to think of this as an instability of Schwarzschild, because if I perturb it along here, because we're doing this symmetrically, of course, if we perturb it along here, it changes the late time behavior of the space-time gets changed, right? And there's a different scaling exponent towards the singularity, right? So this is the sort of generalized RG flow, if you like. So just to make that more concrete, this is how it goes with equations. I mean, we consider the simplest case. I'm sure maybe interesting things happen if you consider more general cases. So we're going to start with ADS-Schwarzschild. So that's gravity plus a cosmological constant. And then we're just going to add a massive scalar field where this mass, of course, determines the scaling dimension of the dual operator. So you can pick it to be relevant. And then we're going to look for planar black holes. So that's solutions that look like this, right? There's a time direction, the radial direction, and the boundary directions. And for historical reasons, I'm fond of four-dimensional ADS, but of course you can do this in other dimensions as well. Right, so we deform the boundary by a source, and then you can just solve the ODEs. So even I can solve them numerically. And so here's a plot of the sort of thing you get. So this is the coordinate, the radial coordinate, right? This is the boundary, this is the singularity, this is the horizon. And here are various, for reasons you'll see, I'm plotting certain derivatives of the field. So for example, the scalar field phi, this is the derivative of the scalar field, okay? It started at 0 at the horizon, sorry, at the boundary, and as you go into the interior, it's constant. So if z d phi dz is constant, that means that phi is going like log z near the singularity, okay? And what these things mean is that the various metric components have certain power law behavior towards the singularity, and that's the scaling fixed point that I'm telling you about. Okay, so this is just to show you that you can trivially solve the differential equations coming from here using these. I saw a raised hand. I'm very happy to answer a question now.
Hey, Sean.
Yes, hey, Blaise.
I was just wondering, why in this case don't you have an inner horizon? Because in principle, now you have a source on the boundary, so you could imagine possibly being able to...
No, okay, very good. So we will come to inner horizons shortly, but in these neutral cases, no, I don't think one expects an inner horizon in this case. I know with axions, you can get inner horizons because those are secretly a bit more similar to to Maxwell fields, but there's no inner horizon here.
Yeah, but it's obvious that there can never be
let me come back to inner horizons later. Okay. So there are no inner horizons here, and so that the Penrose diagram really looks the same as it did before. Okay, it's just that the way the metric behaves near the singularity is going to be a bit different. And so here we see this plot is meant to show you that the scaling, this is the whole RG flow, right, from the boundary to the singularity. And so if you look near the singularity, you can do a coordinate change and you'll get what's called a Kasner metric. So tau is now the approach to the singularity at late times. And so it's the proper time. So we have minus d tau squared. So tau is like z, okay? It's what was the radial direction and now the approach to the singularity. And there's some scaling exponents. So t is now a space-like direction inside the black hole in x and y. So this is an anisotropic cosmology in t, x, and y with these two exponents. These exponents are actually related to each other. So only one of them is free, which is pt. And pt goes between -3 and 1, where -3 is the Schwarzschild value and 1 is a Windler horizon. And so that there's a scaling form of the metric and a logarithmic running of the scalar field. This asymptotic has, of course, been known since the 70s. It's a Kasner solution with a scalar field. And so what we can plot, for example, is the value of pt, which is this scaling exponent near the singularity as a function of the deformation. It starts when there's no deformation, it's Schwarzschild. It goes up, it goes down, and actually we know that it goes all the way back down to Schwarzschild again for large deformations. Okay, and so that's it really for the neutral case. PT is always negative. What PT negative means is that, so this means that this is GTT. What's GTT? GTT you should think of, remember T is the spatial, it's like going along here. So if PT is negative, it means GTT is growing at late times towards the singularity, which means the Einstein-Rosen bridge, this distance here, is growing towards the singularity, like in Schwarzschild. Good. Okay, so that's the simple story for neutral black holes. Let me just go back to this picture. So you deform the boundary. So point one, deforming the boundary is a very canonical way to induce this instability of the interior. You don't need to like perturb the outside. You just induce an RG flow, and that sources this instability of the interior. And within this homogeneous setup, you flow to a general Kasner universe at late times. Okay, so Schwarzschild is here. We can already see that Schwarzschild is non-generic, right, within this framework. All right, now let's go to charged black holes. So even more dramatic things happen for charged black holes, and as was commented, as Blaise commented a few minutes ago. So in charged black holes, you have Cauchy horizons. So the Penrose diagram of a charged black hole looks like this. So there's the boundary, your two thermofield double boundaries. There's the horizon. But if you fall into the black hole, you find another horizons. These are the interior horizons. And if you go through those, in principle, you can keep going into all these different universes, and the singularity is now time-like. So as has been suspected for a long time, going back to Penrose and so-called strong cosmic censorship, it's believed, and I think in some cases proved, that this is generically not going to happen. This is some very special consequence of choosing a very symmetric initial data, and that generic interiors are not going to have Cauchy horizons, these things. Okay. We'll get a little sense for why that's true later. And so we have a very simple setup in which one can probe that, and we will in a second. And so what's going to happen is that we're going to see that indeed these Cauchy horizons are going to go away, and they're going to be replaced by some within our homogeneous standards, and replaced by space-like singularities. And so that the top of the Penrose diagram is going to look like the Schwarzschild case, with two boundaries, an exterior horizon, no inner horizon, and some Kasner approach to a singularity. But there's an interesting new thing that happens, which is that if the deformation you put on the boundary is very small, it turns out that the destruction of the inner horizon is quite dramatic. And so we highlight this regime, and I'll talk about that in a minute. And we call this the clap of the Einstein-Rosen bridge. I'll talk about that in a minute. So upshot, these in a charge case, can people still hear me? I just got a message that the internet was unstable.
Yes,
Okay.
there's some small blotches, but now it's fine.
Okay. Great, perfect, thank you. So, so the charge case, the endpoint is somewhat similar, meaning that the singularity has this Kasner form. The main new feature I want to talk about is what happens to the Cauchy horizon. And of course, mathematicians don't like Cauchy horizons, because if you do flow in, if you set your initial data here, you flow through to this other universe, and suddenly you need to know what's happening, what's going to come at you from this time-like singularity. Okay, so Cauchy horizons, for people who study PDEs, don't like Cauchy horizons. All right. So let me just show you what happens to Cauchy horizons in this context. So now the theory is going to be this one. So same as before, gravity, some scalar field, but now we also have a Maxwell field. Note that the scalar field is neutral. It'll be charged in a little bit. So the statement here, firstly, the strongest statement is that there is no Cauchy horizon when the deformation is relevant, which means that this mass squared is negative within this theory. And it goes like this. I'm going to go through this a little quickly, but it is quite simple. You construct a quantity that vanishes on horizons. It has an F here, which is GTT. So if you integrate the derivative of this between, suppose, okay, it goes by contradiction. Suppose there were two horizons, an outer and an inner horizon. You make a quantity that vanishes at horizons, and so the integral of its derivative from one horizon to the other has to vanish. But then you just take this derivative, you act on these guys, and you use the equations of motion to simplify stuff. Okay, so use the equations of motion. So you suppose there's an inner horizon, and you can integrate something between the two horizons to get zero. You use the equations of motion, and you get something here that is manifestly negative when the mass squared is negative. And so something negative cannot be zero, and so there cannot be an inner horizon. Okay, so the equalities are only possible when there's no scalar field. All right, so this is a holographic version of strong cosmic censorship. Thermofield double states, generic ones, where you've deformed your CFT by a relevant operator, don't have Cauchy horizons. Okay, it's a sort of holographic version of cosmic censorship. I think people would normally think about, some deformation in space, and what we're doing is deforming the boundary value and flowing in. Okay. And so if there's no Cauchy horizon, then you don't get all these crazy extra universes, and the Penrose diagram is going to be something like this. Now, for irrelevant deformations, which for our simple theory just means a positive mass squared, there can be Cauchy horizons, but only at special values of temperature. Okay, so fine-tuned. And it's easiest to understand this at a linearized level. So basically, imagine that you have, here's your, oops, sorry, I'm going to go back again, excuse me. I know this is getting a bit crowded. Why don't I just erase some of this? Okay, very good. So suppose here you have the inner horizon, the outer horizon, and the inner horizons. Now suppose you deform it by a scalar field. The scalar field comes in. We're going to have to impose regularity of the scalar field here, right? At the inner horizon, we're going to impose infalling boundary conditions or something analogous to that. And so you've imposed regularity here. That eats up all of your constants of integration. So by the time you get to the next horizon, you can't also impose regularity at this horizon. And that's why typically, if you have the outer horizon is regular, the inner horizon can't also be regular, because you don't have enough degrees of freedom to impose regularity at both boundaries. However, of course, for certain temperatures and masses of the scalar field, you might be able to have regularity on both sides. So that goes like, so let's imagine putting a linearized scalar field in the Rice-Nordstrom background. Okay, so you put a scalar field, and then you ask for it to be regular at both horizons of the inner and the outer horizon. And that's a boundary value problem, right? And so this is the wave equation. Okay, and so you're asking basically for it's not quite, but essentially normalizable. So it's like, so here's the inner horizon, so outer, inner, and you want to solve the third equation in here with it being regular at both of these. And so this is the wave equation, and this F is negative because you're inside past the first horizon. So this is negative. So this is a positive operator. And so clearly when the mass squared is negative, there won't be any solutions to this equation. That's the theorem from before. But when the mass squared is positive, there will be solutions to this equation at discrete values of the mass for a fixed temperature. And so it is possible to just put a scalar field that's regular at both horizons at discrete values of the mass. Or if you fix the mass, this happens at discrete values of the temperature. And so that's a linear argument. You can verify that it extends nonlinearly. And so you can have Cauchy horizons at certain discrete temperatures for a fixed mass. Okay. All right, so that's fine-tuned. So let's assume there's no Cauchy horizon. And then the Penrose diagram looks very similar to in the neutral case. So the causal and singularity structure, just like the neutral case. And so again, there's a Kastner regime close to singularity, but actually the exponent turns out always to be positive in this case, not negative. And so that means that now as you approach these Kastner, these singularities, the Einstein-Rosen bridge is collapsing, not expanding. Okay, so GTT is getting smaller as you go towards the singularity. I'm emphasizing this because people have associated the behavior of the Einstein-Rosen bridge with complexity and stuff like that. So it can go both ways. And so here, maybe not too important, there's a plot of PT. Now it's a two-dimensional plot because we can vary the strength in units of the chemical potential. That's like the gauge potential at the boundary and the temperature over the chemical potential, whatever. We've made a nice plot. Maybe one thing to highlight, remember in the neutral case, when we turned off the source, PT went to -1/3, which is the Schwarzschild value. Here, when you turn off the source, PT goes to 1, and that's the Rindler value. And that also makes sense because the singularity approaches the inner horizon as you turn off the source. And so it doesn't go to the Schwarzschild singularity, it goes to the inner horizon, which is regular, and that has PT equals 1. Okay. Very good. So the final thing I want to tell you about this charge case is this Einstein-Rosen bridge collapse. So if you take, it's very nonlinear. Okay, so meaning the following, that if I take Weisse-Nordström and I add a very, very small scalar field source at the boundary, the smaller the source, the faster the singularity, the faster a singularity develops. Okay, so let's look at it. And we actually solved this analytically, even though it's nonlinear, and we checked with numerics. So the statement's the following. As you go in towards where the inner horizon would be, okay, so inside Weisse-Nordström, GTT is vanishing linearly, right, as it does at horizons. But instead of actually, before it vanishes, what happens is it goes through this sudden collapse and GTT becomes finite but exponentially small, okay? And the speed with which it becomes exponentially small is 1/phi0, which is the source at the boundary. So when the source becomes very small, this collapse of the Einstein-Rosen bridge, meaning the space-time connecting the two boundaries, happens faster. And so here's a plot. So the blue line is numerics. Okay, so this is GTT in a log coordinate. Here you're going in. The outer horizon is down here somewhere. So you go in, and then it starts to collapse. And then this is it very quickly becomes exponentially small. And the smaller the source is at the boundary, the faster the horizon collapses. And the red line is an analytic description of this collapse that we have. Okay, so I think it's a little bit non-trivial. So we have a exact solution of this nonlinear dynamics. Right, it goes like this. Okay, very good. Let's see. So next up is charge scalar fields, and so if there are any questions about what I just talked about, now would be a good time maybe for them.
I think Oyon has a question. So Oyon, would you like to go ahead with it?
No, I think it's better I ask at the end of the talk, this question.
Okay, that's fine. Did Blaise raise his hand again?
Yeah, sorry to bug you with this again, but this argument you have for no inner horizon, doesn't it depend on the shape of the scalar potential? Because what I have in mind,
of course, very good.
So ADS to ADS domain walls, right, at 0 temperature.
So this is all at finite temperature, but yeah. So of course, so we've taken very good. So we've taken this potential, but of course one consider a general a general action here, and you'll get something a bit different here. And it's not quite the statement. It's something like phi v prime phi should be negative. So something like this,
right?
To exclude. So there's some condition on the potential that will exclude horizons.
Okay, so this would be evaded for ADS to ADS domain walls. Then you would have an inner horizon there once you heat it up, I think.
Don't know. I'd have to think about it. Maybe. Okay. Yeah, need to think about it. Yeah, but these inner horizons are definitely going to be fine-tuned, I think. So it'll always be analogous to this because there's some wave equation, and you need to have regularity at 2 points, and you only have one constant of integration, and so you can only do that at non-generic points. Okay, so I don't think it's that it just because there's two ADSs, it's going to have an interior horizon. All right, so now let's come to the most fun of all, which was so now charged horizons with charged scalar fields. And we could have a source on the boundary, but a nice thing about charged scalar fields is you actually don't have to put them in. Sometimes they just appear spontaneously. And so in this case, the Cauchy horizon is going to self-destruct. Okay, so let me just very quickly remind you how these holographic superconductors work. So you have your charged charged black hole just sitting there. If you have a charged scalar field, what can happen is there'll be pair production, which, by the way, is completely classical as a wave. It just means you have a positive mode going one way and a negative mode going the other way. So, but okay, it's easier to use this language of pair production. So you can pair produce. So you have some negative charge here, some positive charge here. The negative charge gets sucked towards the horizon, and the positive charge gets pushed away. Right. So the negative charge that falls into the horizon will discharge the horizon, and this positive charge gets pushed away. And then it depends how heavy they are. If the scalar field is too massive, then this one will also fall back into the black hole. But if the scalar field carries enough charge, then its electrostatic propulsion from the horizon stops it falling back in, and it just ends up sitting here outside. Okay, so there's sort of this pair production process which can discharge the horizon, and you're here with some. So this is a scalar field, a charged scalar field condensate sitting outside the horizon, and that corresponds to spontaneously developing an expectation value of the dual theory. Okay, so suppose you have this charge outside the black hole. Okay, and so this happens below some critical temperature, and so if you're at temperatures close to TC, but just a little bit below, then the charge outside the horizon is uniformly small. Okay, there'll be some. So here I drew it totally discharging, but what happens right below TC is most of the charge is still in the black hole, and there's just a very little bit of scalar field outside. So we're going to see that tiny little bit of scalar field outside has very dramatic effects on the interior. So first, we have a better theorem. So there's no Cauchy horizon. In this case, there's basically never a Cauchy horizon. So for either sign of the mass or any potential. And I won't write it in equations, but it is a pretty short argument. So we have a charged scalar field. It turns out when you have a charged scalar field, if you want a regular horizon, AT has to vanish on the horizon. Of course, this is in some gauge that I'm using. And roughly because there are terms like phi squared AT squared for a charged scalar field. And it turns out that for regularity, when this is non-zero, it forces AT to be zero at the horizon. It's true, just believe me. Okay, so AT, so step one is with a charged scalar field, regularity. Of course, there could be singular horizons or something, but for a regular horizon, AT has to vanish. That's the difference, I guess, with so if we were mathematicians, we'd have to worry about non-differentiable horizons and stuff. But if the horizons are sufficiently regular, then AT is zero. And then the second step is that with AT being zero, if you had an inner and an outer horizon, it turns out these have to have the same values of ST. If AT were not zero, then actually it's different. It's something like ST plus AT times the electric field would have to be the same on both horizons. But this term is not there. And so this is some version of a first law, integrated first law, small relation that holds. So you can also prove within this context of homogeneous planar horizons, that ST has, if AT vanishes, then ST have to be the same. Of course, Rice-Nordstrom avoids this because for Rice-Nordstrom, AT does not vanish on the horizons. Okay, it's only with a charged condensate that AT has to vanish. So ST has to be the same, but this temperature, which is this surface gravity, is positive for exterior horizons, but negative for interior horizons. And something positive can't equal something negative, and so it doesn't work. Okay, so there's a pretty general argument that you cannot have an inner horizon with the charge scalar field. Okay. All right, so it's easy to put equations to these things. Right. So I mean, yeah, let's leave it at that. So okay, so T is, I mean, it's not, I'm calling it T, but what I really mean is something like F prime, the derivative of GTT at the horizon, right? And when you have two horizons, let's say this is Z, there's a horizon there and a horizon there. F is positive, GTT is, well, F is positive outside, it changes sign, right? And so the derivative of F has different signs at the two horizons, okay? And that's what is not possible. Because this relation says that F has, the derivative of F should have the same sign on both horizons. Okay, so once again, this charge scalar field that spontaneously appears, it will destroy the inner horizon of Rice-Nordstrom. And once again, there's going to be a collapse for a small scalar field. There'll be a collapse of the Einstein-Rosen bridge, and there'll be a Kästner singularity. But it turns out that with the charge case, some fun stuff happens in between, which I want to tell you about. How much time do I have?
It's about a little more than 5 minutes.
Okay, very good. Okay, perfect. So let me just first draw you a picture from some numerics. So this is the boundary. This is the singularity. This is Z in units of Z horizon. So let's, if we can zoom into here. Okay, so this is kind of zoomed in, but the blue line is log of GTT. So this blue going down suddenly, that's the collapse of the Einstein-Rosen bridge. Okay, so again, let's be just below TC. So the scalar field is very small everywhere. It's uniformly bounded outside the horizon. Okay, it's small, but as you go in, as you get close to where the inner horizon would be, the scalar field produces this nonlinear instability. GTT suddenly collapses and gets very small, exponentially small. Okay, because it's a log of GTT. But now in the charge case, while that's happening, the scalar field, which is this orange line, actually it's phi prime, but it doesn't matter, starts oscillating like mad, okay? And so what are these? So actually these are, as a nice thing, these are actually Josephson oscillations, okay? Because what do we have? So remember that Josephson oscillations are when you have a gradient, when you have a superconductor with a gradient in the phase, right? The phase is different in two regions, then that induces oscillations in time of the condensate, of the amplitude. And that's exactly what's happening here. There's an electric field going through the interior. That electric field means that the AT is changing. Okay, AT and the phase are gauge equivalent to each other, right? So there's a varying phase due to the electric field, and that varying phase triggers oscillations in the condensate. Okay, so as soon as you go past the horizon, and actually these oscillations get stronger as T gets closer to TC, the instability gets stronger and these oscillations get stronger and stronger. Okay, so there's some very strong oscillations immediately behind the horizon. Then well, not immediately, a little bit in, but behind the horizon, close to the inner horizon, in fact, would be inner horizon. And then these oscillations die out, and then you have a Kästner regime, and then you think you're done. But if you run it in numerics for an exponentially long time, of the Z time, not proper time, but the Z is a physical, this all happens in a finite proper time, but Z is a perfectly reasonable time, and it measures how much the transverse directions have collapsed. So the transverse directions undergo many e-folds of collapse, nothing happens, but then suddenly GTT is, GTT is growing, the Einstein-Rosen bridge is growing, and then after many e-folds of collapse of the transverse directions, GTT turns around and starts collapsing. Okay, so there are two new things here relative to the case with a neutral scalar. One is these oscillations, and second, this thing that we call a Kästner inversion. Okay, so if GTT is, if the Einstein-Rosen bridge is growing, eventually, after an exponentially long time, it turns around and collapses again. Okay, and so we have analytic descriptions of everything of these in the limit of a small scalar field outside. We have analytic solutions for these oscillations and for these inversions. And that allowed us to understand something pretty, I think, quite interesting. So as t is going to tc, okay, remember outside, that means the scalar field's getting turned off. These oscillations get stronger and stronger just at the would-be inner horizon. And that means that when you evolve all the way and you extract this Kasner exponent, there's some pt here, okay? This pt is a non-analytic function of t over tc. So as t goes to tc, the near singularity behavior is non-analytic in t minus tc, okay? And actually it has this form. So alpha is related to pt, okay? It's some exponent near the singularity. It oscillates stronger and stronger. It's cosine of 1 over t minus tc as you go to tc, right? So here these are analytic solutions superimposed on numerics. So this is, as t is going to tc, right? We're getting really close to the critical temperature. And this is, pt is a function of this alpha, okay? The final pt is oscillating non-analytically, okay? So there's a non-analyticity as you go to tc, which is kind of interesting, I think. So that's where the outside is most boring, the inside is the strongest. And actually that's not all. If you zoom in here, okay, where alpha is this alpha is some exponent, okay, near the singularity. In the regions where alpha goes through 0, okay, it turns out that this inversion becomes stronger and stronger, okay? And when this inversion becomes very, very strong, it actually induces a new set of oscillations, all right? So let me maybe draw it here, right? So we have, as a function of z, GTT is growing, and then for these, oops, I'm sorry, for these special values, the Kasner inversion becomes extremely strong, and actually it triggers a whole new set of oscillations, and then the whole thing just repeats itself again. And actually there's a fractal structure that if you zoom in on certain spots, you can go for arbitrarily long. Okay, so there's near the zeros of this exponent, there's a Kasner inversion that becomes increasingly sharp. They seed further Josephson oscillations, and the whole thing repeats recursively. And so for certain fine-tuned temperatures, you can get an infinite number of scaling epochs separated by violent oscillations. So that's my terrible picture of that. And so as t goes, these special temperatures accumulate as t goes to tc. So there's an infinite chaotic structure of the interior, while the exterior holographic superconductor is just sitting there in equilibrium. And for this behavior, these oscillations were crucial. It only doesn't happen for neutral scalars. Okay, so I have 2 pages of conclusions. I'll go very quickly. So I started saying that if you deform a CFT by relevant, but you can also, or irrelevant operators if you want, works as well with a cutoff. That gives you a more generic thermofield double state. And the duals of these states have an interior Kasner singularity that's characterized by an exponent PT. In the charge case, these more generic black holes typically don't have a Cauchy horizon. And instead of a Cauchy horizon, they have this thing that we call the collapse of the Einstein-Rosen bridge, where GTT, remember, GTT is this direction, right? It's what's connecting the 2 sides, becomes exponentially small over a time scale that vanishes as you take the source to 0. So it becomes more and more abrupt. When you have charge scalars, then in addition, you get these Josephson oscillations and inversions in which PT changes sign. There's a non-analytic dependence on the singularity as t minus tc goes to 0. And for certain temperatures, you get this chaotic sequence of Kasner regimes at specific t. Now, for some people, that might be ringing bells because there's a very famous, these BKL epochs. But it may be that they're going to be unified at some point, but this is not equivalent. It's not equivalent to that, even though it has a very similar flavor. And because the charge of the scalar is absolutely essential, these different epochs are triggered by these very sharp oscillations. And as far as we can tell, they're distinct from these known cosmological billiards chaotic dynamics. Of course, looking ahead, what we've done so far is giving you some tractable examples of rich stuff that can happen in the inside. And of course, one would like to probe that from the outside. Just a little bit of bad news is it's not easy. So for example, these entangling surfaces of Hartmann and Maldacena, for example, they don't actually go very far into the horizon. And most of in fact, all the interesting stuff happens a bit further in. And so it's not completely trivial to probe it from the boundary, but I would encourage everybody to try. And once we can probe it from the boundary, there'll be a lot of rich CFT physics to uncover. All right, thanks a lot for listening.
So thank you, Sean, for this very interesting talk. So let's unmute ourselves and clap. So let's open the floor for questions and comments. So I already have a question. Yes, please go ahead.
Hi, Sean. So I don't know whether I'm asking a silly question or not. So would it be correct to say that it is a bifurcation point would be the place where you are triggering the change in the dynamics of the interior, and hence somehow there would be some sort of a membrane paradigm would know a little bit about what is happening about the interior too?
Let me, sorry, say, let me see. I didn't quite get the question. Are you asking whether sorry, say that one more time. So are you asking whether the membrane paradigm for the exterior horizon would know about the interior? Was that?
Yeah, at least up to the interior, whether there's a Cauchy horizon or not. Maybe if not completely about the interior, because.
Well, let's see. Okay. I don't know. I mean, let's see. Sorry. The interior horizon is not close to the exterior horizon, so I would suspect not actually. But I mean, I thought you also. I don't know whether there could be a membrane description of the interior horizon. Actually, maybe that's possible. I would doubt that a membrane description, because that's really based on what's happening outside, right? So I suspect not, but okay.
Well, but suppose you can just take the Schwarzschild one, this is Schwarzschild case, what would you say? I mean, there would be some kind of membrane paradigm like understanding possible of this interior.
Okay, so let's very good. So the specific, the challenge, so what I would love someone to do is find an exterior description of, so say you start with Schwarzschild and you put in a small scalar and you just treat it linearly, okay? What just the instability is you'll see that phi will start growing logarithmically in the interior, okay? So that's the first thing you'd like to see, okay, is the onset of this instability, which is this logarithmic growth that then the whole thing becomes Kasner eventually. But the first thing you see on Schwarzschild is logarithmic growth. So the question that you'd be asking is whether if I do the membrane paradigm with a neutral scalar field in Schwarzschild, can I see this log Z behavior in the interior, for example?
Yes.
And I would not be optimistic, but it's not a considered opinion, so don't let me stop you. But I mean, I would have thought this is going to be too far away from the horizon just to see it. But
because it's towards a singularity and it is. But I was thinking in that if you trace it back to the bifurcation point, if it is something that
you mean here?
Yeah, if it is, so that is going to affect both the horizon and the interior, right? If you could trace your horizon all the way back to the bifurcation point, perhaps.
I'm going to guess not, but I haven't thought about it.
Okay.
I think my feeling is that to really see this, well, the other issue, I mean, related to things that we did try, is that it's quite a mild instability. It's this log, and it's not totally trivial to pick it out from other things that might be happening. And I doubt that it's really developed here, but
okay.
By all means, think about it some more. I don't think so, but it's worth thinking.
Okay, thank you very much. Thanks for the nice talk too.
So more questions and comments for Sean?
I have Arnab, I have a question.
Sure, go ahead.
Sean, can you comment on planar versus spherical?
Yes. Let's see.
Spherical horizons. Most of your talk was about planar.
Yes, that's right. And I like planar horizons. Let's see, and that also made the scaling behavior a little easier. Yeah, let me let me see. So there was actually, so in terms of the yes, and so let me say one result that I know exists. So in terms of this charge scalar field, there was a paper by from Beijing showing that actually this theorem does extend to spherical horizons, and not completely trivially, so it does extend. So that's one statement I can make. In terms of the, oh yeah, right. So yeah, I think the near horizon, the near singularity behavior will be the same because the curvature, I think, doesn't become important close to the singularity, but it might be a bit harder to write down the metric. So very good. So I think the Kastner thing is also true for spherical horizons. Now, what I don't know about is whether more interesting stuff could happen in the middle, whether they're, qualitatively new regime. I mean, you have an extra scale, right? So when there's a spherical horizon, there's an extra scale in the theory. So even in a neutral case, okay, very good. Upshot. I suspect that the neutral case, the story is pretty similar, but okay, someone should check. For the charge case, there will still not be spherical horizons. I don't know what happens to the charge case with the neutral scalar. So I have no reason to expect anything qualitatively different, but someone should check.
Okay, thanks.
Okay, so any more questions or comments? If not, then I can ask probably something which is very, very naive. But let me understand this. So the most of the or all of the calculations that you're doing are in Lorentzian, right? Because you're describing a horizon and it's outside and inside. But in terms of the CFT, what should I understand? That I'm actually perturbing a CFT state which is thermal, or how would we see this deformation?
Okay, so no, so in let's see, so in these cases where we have an explicit deformation, it's literally this, right? So it's just like you would in an RG flow. You take sorry. Let's talk about the action, then we can talk about the state. All right. So firstly, in terms of the theory, right? You take your whatever your theory is, and you just add this deformation with some operator, right? That's certainly something you can do to the action. That theory then has a thermofield double state, right? And so what we're doing is taking the thermofield double state of this theory.
I see.
And what holography does is sort of construct that for you. Lorentzian, right? So indeed, you construct the Lorentzian background, and right, and it's this.
I mean, the reason I was asking is because, I mean, at some level, the thermal states or even thermofield double states are in, I mean, it's true that you need, for the thermofield double, you do need the two-sided Penrose diagram. But for a thermal state, what we ordinarily do is just do the Euclidean, you just stick to the Euclidean description. And,
no, that's right. Mm-hmm. So you would definitely create, so you would create these, and these would definitely be created in the same way, with this sort of Malacina, or whatever it is, Hartnoll-Hawking instanton like thing, right? So that you create this, you could these are the states that are created in the same way, just with slightly different boundary conditions. But then we're asking about the evolution, right? And so the evolution, so you want, to probe this, you need to ask questions, right? Good, thank you. So of course, this is this usual story that there is, this whole thing is time translation invariant in terms of t goes to t plus t. But if you keep the t, but the t is running in the different directions on both sides, right? So if you ask questions about something here and something here, and you move that around, that'll be t dependent, right? That'll be, so there is a time dependence in the thermofield double state if you ask this question about moving things in the same direction on both. For example, this entanglement entropy, right? So there's a certain surface that you construct that goes something like this. And as you move these points forward, well, as you know, yeah, that surface changes, right? And so that time dependence is sensitive to the time dependence in the interior.
That's right.
Yeah. So totally, yes, you can definitely create these things with the Euclidean instanton, but you can also ask questions that sort of reveal this time dependence of the interior.
Okay.
Even though, yeah, T goes to T is a symmetry, right?
Right. So in that sense, is it possible to sort of see a signal? I guess this is also your last point. But
say that again.
So is it possible to see the signature of this Kasner physics from the CFT perspective somehow, or?
So we sort of did it in this first paper. Okay, good, wonderful. Seeing as someone asked, let me. So there are different probes you can do. I think the currently existing nicest one is this entanglement entropy one, because there you're really calculating something very physical. It's more or less physical. It's an entanglement of certain. It's a well-defined entanglement you can ask about. Now, you can also, but those surfaces don't go near the singularity. So you can prove, I think Aaron Wald and others might have proven that these surfaces, quite generically, there's a critical surface here, and these entanglement surfaces cannot get close to the singularity, and so they never see the Kasner regime. Okay, they also don't see anything interesting that I talked about. Doesn't seem to be easily seen with these. Now, you can also try to construct geodesics, and those sometimes can bounce off the singularity. And if you treat them sort of naively, you can see aspects, you can extract the Kasner exponents from these guys. However, they're not very satisfactory for two reasons. So one is that when you do this, what you're actually computing is this Schwinger-Keldysh-Green's function, G12, from the two boundaries, right? And it's just a theorem that in the thermal state, G12 is related to something, is all the information you would get from that is also in the retarded Green's function of a single side. Right. There's some imaginary part and there's some Cauchys and exponentials and stuff. So it's probably a bit of a fake. So I mean, it's really a property of analyticity and the fact that the differential equation is second order and stuff. So you can see things in the 2-point function that do depend on the singularity, but you could equivalently have done the calculate. If you could do the calculation exactly, you could also do it entirely in the exterior. And so it doesn't really feel like a very good probe with a singularity. And there's also this problem that's problem one, not a problem, but it's just fact one. And whilst this entanglement surface is different, the entanglement, there's no other way to calculate it as far as I know. And the second problem is that these ones that bounce, the geodesics that bounce off the singularity actually don't dominate the Green's function. And that was in this paper by Schenker et al. From some years ago. So that it turns out these geodesics that bounce off the singularity are not, only give some very subtle, if any, some very subtle subleading contribution to the Green's function. So I don't know, at the moment, I do not know of a nice probe that sees this Kasner regime. But I certainly hope, I hope it exists, but yeah.
Okay, thanks. So any more questions?
Yeah, I have probably a very quick question on the same thread as Arnob. So you would not also think the quantum extremal surface could do it in principle?
That's fantastic. Yeah. So I don't think, right. I think that this theorem is for the classical surfaces as far as I know, and quantum extremal surfaces and islands and I think it's definitely worth thinking. Yeah, definitely worth thinking about. Yeah, I whether you can do something that would sort of bend these surfaces up so they can see into the interior. Definitely interesting question. I hope so. So in fact, based on the fact that it's not totally trivial to see these to get into the interesting regime. I mean, it might be that to to understand this near singularity thing, you really have to do something a bit more non-trivial that's related to what you have to do to understand how the information gets out of the black hole and all these things. So I think it would be great, it'd be cool, and maybe has a chance of being true that some of the same sort of things that help you understand how the information gets out can also help you probe the more near singularity region. But we haven't done that.
Thanks.
And another, while I'm at it, thing to have in mind is whether there's some completely different dual description that lives on the singularity somehow, right? And that this scaling, the scaling behavior might suggest there's some simplification of the dynamics near the singularity that, maybe actually, and to say something that I know people has been said before, but maybe not everybody's heard it. I mean, this is all homogeneous. If you have inhomogeneities, actually what happens is every point in space kind of breaks up as you approach the singularity. And that has a bit the flavor that maybe the matrices are trying to reemerge, or so, the space-time is breaking up and you can go back to some kind of matrix gauge theoretic description. And so maybe there's some, dual matrix-like description near the singularity that would be also, of course, be pretty nice. Yeah. Oh. That's just a speculation.
Thanks.
Okay, great. So I guess we can also continue with the question on the.
Can I have a quick query, Tushan?
Oh, yeah. Okay, sure.
Actually, I missed a considerable portion of his talk. Sorry, I don't know whether I am asking a relevant question. But I mean, this setup. Do you think that these setup are also compatible with three-dimensional ADS gravity?
Oh yeah, I definitely. Actually, so I didn't mention 3D, but we looked a little bit at it, but there's nothing in the papers. Actually, yeah. So 3D, for example, 3D Schwarzschild, the singularity is kind of a bit fake because it's just a quotient. But actually, once you put the scalar field in, you do get a legitimate singularity in 3D. And maybe it's possible to do things even more explicitly in 3D. But yes, this framework and questions can definitely also applies to 3D. Yes.
Yeah, because in 3D, I mean, there is a regime like BTZ, 3D BTZ black hole. There is a regime where actually SCC gets violated.
Yes. But I think these perturbations will probably kill the inner horizon.
Okay.
Most likely, but yes, yeah, right. But yes, yes, right. Actually, we have a few comments about the 3D case. That particularly, specifically that question in the second paper. I mean, there's not a lot, but there's a couple of sentences about the result you just mentioned.
Okay, thanks, Sean. So I guess, of course, I mean, feel free to continue this in the Slack, but let's again thank Sean for a wonderful talk.
Thanks, organizers.
This closes this session, and the next session is in about 3.5 hours. So till then, I guess, enjoy.
Thanks, Arno, for conducting this, and thanks to everybody, to all the speakers and participants. See you in a while then. Bye.
Okay, right. See you. Thank you.